Good morning, everyone. Welcome to day 3 of the Modelling, Analysis and Inference for Digital Twins workshop. We've got another set of fantastic speakers lined up today, the first of which is Rich Wilkinson. Rich is a professor of statistics at the University of Sheffield and widely recognised as an expert in uncertainty quantification and emulation. Over to you, Rich.
Thank you very much. Thank you for the invitation. I've really been enjoying the meeting. So what I thought I'd talk about today is some work on trying to create a digital twin of the air pollution in Kampala. Although I'll freely admit I've never called it a digital twin until just now. Okay, it's the first time I've used those words in public. But essentially what we want to try and do is build a model from a network of sensors we have around Kampala, and to represent the level of the air pollution in the city, and to update that in real time to enable the policymakers and the public to make decisions about whether they go out for the day, whether the pollutions are very high, what they could do to change the pollution levels to improve things, what's causing the pollution, and so on. So it sounds like a digital twin. So this is joint work with a large team of people. So Patern Gahungu and Chris Lanyon are the first authors on this particular bit of work, but it's with Mauricio, Mike Smith in Sheffield, and engineer Baina Magisha in Kampala. And we were originally funded by DCRF and EPSLC, but we were on one of those unfortunate projects who, when the pandemic struck, were cut and terminated early by the government. So they just cut all the DCRF projects halfway through, basically. Thankfully, we had some other funding from Google that's allowed the team in Kampala who collect the data to kind of carry on and build this network. Okay, and the other problem we had was, of course, this was about deploying a network of air pollution sensors. So the first thing that happened, we were just starting January 2020. So there was a lockdown straight away, so we couldn't deploy sensors in the same way. Then there was presidential elections, so the internet got turned off for an extended period in Kampala, and so there's all kind of things that delayed us collecting data. But now there's up and running, and there's lots of interesting things coming in. So what I'm going to talk about is just a kind of general problem and our modelling approach that we've taken, and then I'm going to abstract it and just talk about inference for linear systems. So something where we've got some unknown with modeling, which we're called U. We've got some kind of linear model, differential equation type thing. And what we want to infer is something about what's driving this model, the source terms. And I'll talk about one particular trick that we've been using based around these adjoints. Okay. So it's not going to be a very technical talk, but I will kind of explain what adjoints are. I know not everyone's familiar, and certainly I wasn't until we started using these things. Okay. So just to say a little bit about air pollution, it's a huge problem. It kills about 7 million people every year, we think, which is approximately the same number of people who die each year of cancer, for example. Okay, about the same number of people who've died in total of COVID. So it's a huge problem, and it's a huge problem in the West, global North countries and global South countries. But it's a much bigger problem in the global South. So countries like India, China, and sub-Saharan Africa, air pollution is far higher than, say, the UK. But even in the UK, the government estimates it kills about 30,000 people in the UK each year and costs the economy about £10 billion a year. Okay, so hugely impactful on a whole range of kind of different medical conditions. So it's much worse in Kampala for a variety of reasons. So Kampala is the capital of Uganda. Okay. They have older vehicles, more polluting vehicles. They're often, inefficient industries, but then they have things that we don't really have here. So people tend to cook at home on solid wood fuel stoves. There's a lot of burning of garbage, people at home. Unmade roads often, which throw up a lot of dust. Okay? So there's lots of reasons why pollution is worse in sub-Saharan Africa. So the way we monitor air pollution in the UK and most kind of rich Western countries is via these gravimetric sensors that cost tens of thousands of dollars per sensor. Okay? That's not feasible in places that are less wealthy. And so what Aircrobe are doing, which is an organisation set up by engineer Baina Magisha, who we're working with, is they develop these cheap, low-cost air pollution sensors. Okay? So these cost about $40 each to make. Okay. And we've deployed them all around the city. And we try and do the best we can with this kind of lower quality data. We know these sensors drift off their calibration, so we get poor measurements sometimes. We know they break down all the time. So we do a variety of things to try and keep them in check. So one of the things we do is we attach them to these boat drivers, these are motorbike taxis, and we pay them to drive around the city. So they might go to the one expensive sensor we have at the US Embassy, calibrate their sensor there, and then drive around to the other sensors, and we try and post hoc correct all the data to do the best we can with it. Okay. So these are the kind of data we get out. So you can't see the numbers here, but there's a kind of color chart on the bottom from the World Health Organization. So whatever units I'm using here, microgram per meter cubed, this is PM 2.5, which is a particular type of air pollution we're measuring. Okay. So good is anything kind of under 10. Okay. And then you can kind of go up this scale. So you can see Kampala nearly all the time is in this unhealthy zone with, advice not to exercise outside, to limit your activity outside and so on. And often it gets into a very unhealthy zone if the weather conditions are heavy. Okay. So just for comparison, the numbers here are like 70 to 150-ish. Okay. The average for London last year is 8 milligrams, micrograms per meter cubed. 20-year average for the UK is about 11. Okay. It's going down all the time in the UK. So you can see even here, we're still above the World Health Organization guideline, what they'd like of 5, but we're a long way from the kind of numbers we see in sub-Saharan Africa. Okay, so the aim of what we're trying to do then is to build a model to understand the air pollution here. Okay, so to say, what the air pollution is, but also to help policymakers. The air quality team work with the Kampala Capital City Authority to stage interventions to see what's going to happen. So just last weekend, they had a traffic-free day and shut many of the roads in the city. Okay? And we can see what happens to air pollution and try and get a better understanding for things. So that's our aim and our reason for modeling here. So what we want to do ultimately is we want to learn the pollution concentration, which I'm going to call U, okay, which varies in space, x, okay, and time t. We want to infer what it is everywhere and say what's causing it. Why is this pollution here? What could we do to make the pollution less bad? Okay. So a common thing done with these kind of data is to interpolate everything using a Gaussian process or some sort of a non-parametric model to smooth out your data, to say what it's like everywhere in space, fill in the gaps in your map, okay, in space and in time. But part of the problem with that kind of approach is it doesn't allow us to say anything about the pollution sources. Okay? We are not able to say what's causing the pollution, and these models are kind of naive. They don't know anything about how pollution moves. So what we're trying to do instead is build models that do know some physics, do have some idea that pollution behaves in a certain way. So this is an advection diffusion reaction equation. So this says, pollution gets blown around by the wind. Okay, it advects. When the wind blows, it moves across the city. Okay? It diffuses, so it goes from areas of high concentration to low concentration. It reacts with stuff, so it sticks to trees, it floats off into the atmosphere, it sticks to the ground, whatever. Okay, it disappears, and it's caused by stuff. So this is kind of what we're interested in: is what's driving this thing? What's the different pollution sources? Okay. So kind of the hypothesis we're trying to test is, do partially mechanistic models like this help us predict better? And we know this is not a fully mechanistic model because we basically model the city as a square. We include all the kind of interesting topological information. It's just saying, if we include some sort of diffusive type behavior, does this improve our predictions? Okay? Does it allow us to say anything interesting about the sources and so on? So,
Do you mean that it counts with the geometry of the building?
No.
Sensors are down, they're not above the building.
No.
So you're like flow around the city.
Yeah, we've got none of that. We're basically a flat, and we're going to see if this model helps. Okay, so we know about the wind, but obviously this is just we know nothing about the buildings, the trees, topology. We're not including any of that information. We couldn't possibly model that kind of detail. Okay, and So what we want to do is given some sort of noisy measurements, so I'm going to call them Z here, of the pollution. So maybe they're snapshots of pollution at different locations at different times. Can we learn concentration fields, source terms, etc.? Okay, and all these additional terms. How do we solve that kind of statistical challenge? So what we're going to do, we're going to model the source terms. These are the driving pollution sources in our model as Gaussian processes. And in theory, what we'd like to do, we haven't actually done this, but in theory, we'd like to have this as a sum of different types of sources. So we have data on different types of pollution, PM2.5 and PM10. We know things about the city, which we could, in theory, at least build into prior distribution. We know where the power stations are, where the poorer neighborhoods are, and so on. We haven't actually done that, but that's kind of our ambition when we set out. Okay, sorry, let me try some water. Oh, thank you, Chris. So just to abstract then for a minute, we're just going to talk about inference here for general linear systems. So we've got some kind of linear operator on this thing, and we want to infer our F here. So it's one particular trick we've been using, which we think is quite effective. Okay. So just to express the situation, we've got a linear operator, okay, which maps upon our unknown pollution source or our unknown thing, okay? And we're supposing this is systems driven by some forcing function F. Okay? So given a system like this, solving this for you, given F and any parameters we have floating about, is the forward problem, solving our PDE. Okay, that's fine, we know how to do that. What we want to do essentially is given noisy measurements of U, go backwards and infer F and maybe the parameters, maybe the pollution field everywhere. Can we go backwards from this and say what P is, F is, U is, etc. And our starting position really is that MCMC is going to be impossible for us here. Thanks, Chris. MCMC is going to be impossible because it's just going to require too many forward solves. If you think about it, every step of your MCMC algorithm is going to require a new solve of your forward system, and that's going to be quickly grow too computationally expensive for us. So what kind of approach might we want to take? Well, there's a variety of things you might want to do. You might want to solve the least squares problem. So that would be to choose your P and your F to minimize the sum of squared errors between your data and what your model predicts, subject to your model being obeyed. Okay. Or we might want to take a Bayesian approach and find the posterior distribution for F and the other things. So they're the problems we're going to solve more efficiently. Okay? And adjoints are going to help us do this. Okay. So if you're like me, you've long forgotten, even if you ever knew what an adjoint is. I know the other speakers were talking about adjoint sensitivity the other day, and it came up in a variety of talks. We're not going to talk about adjoint sensitivity particularly. We'll use them in a different way. But just to say what an adjoint is, okay, and if you're a statistician, there's a really nice kind of pedagogical style paper by Don Estep that walks you through much of the functional analysis here. So let's suppose we've got two Banach spaces, okay, so they are vector spaces with a norm, with a distance, a size associated with them, okay. So vector spaces, they might be spaces of functions or of, Euclidean vectors or whatever, okay. And then we've got some linear operator between those spaces. So in our case, we've got a space of functions, that's how we model the pollution concentration, and a differential operator that's going to map to a different set of functions. Yep. Once you have an algebraic space, a Banach space in this case, we can consider it dual space. So dual space is just a space of bounded or continuous linear functionals on that space. So the dual space takes elements in U and maps it to the real numbers. So it might be a derivative at a point, the value at a point, an integral, something like that. It's a linear map from the functions to space. So what we'll do, we'll construct what adjoints are, okay, very slowly. So let's suppose we have an element in the dual space on V. So that's something that maps from the functions in V to the reals. Okay. I'm going to find a different functional that maps from U to the reals. So for any given U, any given vector, think of a function or a Euclidean vector, we're first going to apply our linear operator, L, to map it into V. And then we're going to apply this functional V star that we picked out. Yeah. So just two processes that we've done. Okay. It's quite easy to show that F is itself a bounded linear functional on U now. So in other words, it is in the dual space of U. Yeah, it's an element in this dual space. It's a linear bounded functional. So it must be equal to some U star in our dual space. So what we've done is for every element in the dual space on V, we've associated a unique element in the dual space in U. Yeah. And that's our adjoint, essentially. Yeah, we've defined a linear map from the dual space on V to dual space in U. Okay. And that's our adjoint operator. Instead of mapping from U to V, like our original operator, it operates backwards from V to U, V star to U. And this is what we're going to use to make the computation relatively cheap. And all we're going to know about it to work out what the adjoint is what this bilinear identity. So by construction, we have this identity holds here that it doesn't matter what order we do things. We can apply L to U and then V star, or we can take the adjoint operator to V star and then apply that to U. So that's our identity that's going to allow us to identify these things. So things are slightly simpler in Hilbert space. We need a more general balanced space, but Hilbert spaces are vector spaces with inner products, with geometry, with angle, as well as distance. Yeah. So if we've got an inner product, tells us the angle and the size, essentially, then in this case, the dual space is isometrically isomorphic to the original space. They're the same space, essentially. Okay. For every element of the dual, we can write it as the inner product with some element of the original space. Yeah. It just simplifies things, whether they're the same space, the dual and the original space. Okay, so that gives us the bilinear identity you probably seen you're more familiar with, okay, that says if we take the inner product of LU with V, that's the same as the inner product between U and the adjoint applied to V. Yep. So it's just kind of the standard definition that you've probably seen for adjoints previously, if you've seen that at all. Okay. So let's just have a minimal example. So let's suppose we've got two finite dimensional vector spaces, so just Euclidean vector spaces. Now, these are vectors of numbers, n numbers. Okay? And the inner product is just one vector times the other, okay, the dot product. And in that case, all linear operators are basically matrix multiplication. Yeah. In this case, the adjoint is very simple. Okay? We just need something that obeys this. If you remember what I wrote down this was in this space, it's obvious that our adjoint operator's got to be A transpose, basically. So we just transpose the matrix. And essentially, the same thing happens when we have more complex spaces. So if these are spaces of functions, we essentially have the same process, and we're going to transpose the operator in some sense to find the adjoint. Okay. So how does this help us? What are we gaining by doing this? Well, let's suppose this is the system we're interested in. We want to learn F, remember? And we've got observations Z that are noisy observations of U. And let's suppose those observations are linear observations of U. So that might be picking out the value of U at some point in space and time. Or it might be integrating U over some bit of space and time, or differentiating something linear, basically, in our concentration field. And what we're going to do instead is, instead of considering this original system and solving this, we're instead going to solve these different adjoint systems. Okay? So it looks like this comes out of nowhere to begin with, but this is going to allow us essentially to say straight away what F is. Okay. So if we think about our observation operator, our observations are HI in a product with U. Okay, just something about U, it's linear. Well, our modeling assumption, what we've done, this trick for the adjoint, we've now said that HI is L star VI, so substitute that in. Then we use our bilinear trick. So this is the inner product of VI with LU. Okay. And LU, by definition, is F. Okay. So we've rewritten our observations directly in terms of a linear thing to do with F. And this trick to make it linear in F is what's going to allow us to learn F very efficiently. So how does it help? Well, let's suppose that F is a parametric model with some sort of linear dependence upon some unknown parameters Q. Okay, so in other words, let's suppose we've got a basis representation Q, or some sort of representation like this. So it's some unknown coefficients, Q, times by some known basis vectors. So if we're in a functional space, these are functions. So we've seen people do this. I did it the other day, and various people, Claudia, had this kind of representation in. So we've seen this kind of thing before. So back to what we just had, if we now take our observations with the unknown product of VI, the solution to our adjoint systems, and this parametric representation of Q, because the inner products are linear, we can just take the Q out the front, and what we get here is a linear combination of some stuff we know. Okay, so this is a linear model, right? Our observations now are a linear combination of some unknowns times some stuff we can know. And statisticians, we know everything about linear models. We can just solve this very simply. Okay, so we write this in a slightly different form, become more familiar. What we've got here is our observations now are some matrix of stuff we can compute times the vector of unknowns plus an error term. So this allows us to change this constrained optimization problem, to minimize the sum of squares subject to our PDE or our differential equation model to an unconstrained problem. All we need to do now is solve this least squares problem with no constraint, and we know how to do that. Yeah, we teach this to the first year undergraduates. Just a formula we can write down to tell us straight away what our posterior, what our estimate is, our estimator that minimizes the sum of squares here. We can also do the Bayesian thing. So if we have a prior mean for Q that's Gaussian, and our observation operator is Gaussian, okay, then we can just write down the posterior as well. We automatically get, for free, the posterior distribution of our unknown parameters, and hence the posterior distribution for our unknown function f. Yep. So it has allowed us straight away to write down the posterior distribution for our forcing term here. Okay. Yeah, so this is just a summary, basically. Given some sort of optimization problem, if we convert the problem to this system of adjoints, it allows us to directly write down the solution to a least squares problem, okay, and directly write down the solution to the Bayesian inference problem. We don't have to do any of the MCMC, quadrature, or anything like that. We just have to do a bit more computation in a way I'll explain. We could also, if we've gone to this effort of working out the adjoint, get adjoint sensitivities that people have talked about, which tells us the derivative of our cost function with respect to the unknown parameters and things like this, which can be useful in second stage inference, but that's much more widely known about. Okay, so how does this work with Gaussian processes? So just who's familiar with Gaussian processes, just so I know? Okay, most people, not everyone, so I'll briefly say. So a Gaussian process then is just a model of functions here. So if you've got an unknown function, a common kind of statistical model is a Gaussian process, which just says the joint distribution of the function at any points has a multivariate Gaussian distribution. And if you don't know the function, a collection of points, or anyway, it's got a multivariate Gaussian distribution. And all we have to do to specify a Gaussian process model is to say what its prior mean is and its prior covariance function. Okay, and so the picture everyone always shows is we start with a collection of a prior model of functions, so some sort of model that says how wiggly they are, how variable they are, how differentiable they are, something like this. And we observe some data, and there's a nice way of getting a posterior distribution here for the functions. So how can we do this? Our adjoint trick with Gaussian processes. I'm going to skip that. Okay. So how can we do this? Well, one way of doing it is by parameterizing the GPs to reduce them from infinite dimensional models to make them finite dimensional models instead. Okay, so what we're going to do, we're going to think about what we're doing when we pick a Gaussian process. When you pick a Gaussian process, you specify a mean and covariance. And what you're doing implicitly when you pick a covariance is you're choosing a space of functions that you believe your function lies in. Okay. So in other words, you're picking what's called the RKHS, reproducing kernel Hilbert space. And this just says things like how differentiable the functions are, how smooth they are. Okay. And we don't really think about that often. We just pick a K. Okay. But that's what's happening under the hood, essentially. We're picking a space. And once we know the space the function's working in, we can think about a basis for it. So that's a set of vectors or functions that span that space. Okay. And once we've done that, we can think about truncating an expansion in this infinite number of terms to a finite number of terms. Yeah. So we're just going to write our Gaussian process as a linear model, essentially, an unknown combination of a large number of functions that we do know. Okay. And what the effect is here is we are approximating the GP by a finite dimensional linear model. It's a very common thing to do. Okay. So how do we pick the basis? There's multiple ways. In some sense, the optimal way is what's called this Mercer basis, but that involves finding eigenfunctions of this operator, which is difficult quite often. Okay, we can do it in 1, 2, 3 dimensions, but 4 dimensions already becomes too expensive and probably not worth the effort anyway. Okay, but the best thing to do mathematically is this Mercer basis. So what we do instead is something much simpler. We're going to pick what is called a random Fourier feature basis. So that works by saying, well, if you've got a stationary kernel, which means like this, your kernel is the Fourier transform of some positive measure. Yeah. And once we know it's a Fourier transform, we can essentially represent our unknown function as a sum of trig terms, cosines, okay, shifted off in period and offset. Okay. So we're going to pick basis functions that are just sums of cosines, essentially, here. And Bochner's theorem tells us what distribution we need to pick for these unknown things. Okay, and it's just a table you look it up in. That's it. We also did more exciting things. So with Steve and Richard, we were modeling doing GPs with data on the heart. And so we want models that know it lives on a complex manifold. And then we can do things like Laplacian bases. So we've got some papers doing that in this kind of interesting cardiac setting. But here we're just going to do the simplest thing. Explain why it doesn't matter. Okay, so just a very simple differential equation model to start with, just to go through the process of how adjoints are computed. This is the kind of thing that was useful for me when I was learning about these things. Okay. So let's suppose we have a simple second order linear differential equation, a pendulum or something like that. Okay. How do we compute the adjoint of this? Well, it's very simple. Okay. If we think about, write this in the notation I had before, this is a linear operator. So the linear operator says differentiate with respect to time twice, times by diffusion or whatever, these things. So it's just an operator that acts upon our unknown function u. So we want to find the adjoint to this operator. And all we do here is integrate by parts twice. So we use this bilinear identity. Remember, bilinear identity said something about the inner product of LU with V. So if we write that down in a function space, this would be a choice of inner product we could use. Okay, multiply by V and integrate. So we have something like this, and all we're going to do is integrate by parts twice, essentially. So I won't go through that, but we've integrated by parts once to shift the derivative, the second derivative on U into a first derivative and transform onto V. Then we do it again to transfer the other derivative on U onto V again. Okay. So integrate by parts twice. And then if we choose the right conditions on V, all the bits we don't like disappear when combined with the initial conditions in U. Okay. And we can see down here, we've got something that looks like another inner product with U. Okay, so this is going to define for us what our adjoint operator is by looking at, by just calling this thing in here L star V. Okay, so it's very easy to compute adjoints, and it's automated in some software, okay, in many cases, I believe. So, you know, it's an easy thing to do. PDEs is slightly more complicated. We need some vector calculus type things, but as I say, it's largely automated. Whenever you're solving things numerically, it's just transposing a matrix, essentially. Okay, just one thing to note. We started with a differential equation like this with initial conditions. This gets transferred to a differential equation with final conditions. So we have to solve this thing backwards sometimes. That's what normally happens here. Okay, so I'll show you some results. The results are kind of pointless in a sense that if you believe what I've told you, it's just showing that it works. There's no convergence plots or error plots or anything like that particularly. It's just showing the method works. So for this differential equation model, what we did, we randomly picked a source term. So that's my curve in red here. Okay. And this top plot, we suppose we have 10 data points equally spaced in time. This is the wrong plot. And we assumed we observed the output to this differential equation. Okay. And can we infer what the thing is? Yes. So we had kind of 100 basis vectors here in our expansion, and with we'll talk about cost in a minute, but this took us 10 solves of a differential equation to compute this whole thing. Okay, so with no MCMC, it just tells us the answer straight away. If we have more data, you learn better. So as I say, it's not particularly interesting, but what we're going to see is that the number of ODE solves or system solves we require is equal to our number of data points. Okay, so it's going to grow in that sense. Just to show what happens if you have too many features. So here I've got 100 data points in both cases. Here I had 100 basis vectors. At the bottom, I just had 10 basis vectors. I say I don't do it. Kristen Patern did all the results. But what we see is we get a model that is misspecified in some sense. When we only have 10 basis vectors, 10 cosine terms, we don't have enough representative power, and we get a model that's wrong and overconfident. And this often happens when we have misspecified models. You'd hope that it'd give you a vague prior, say you don't know anything. What happens instead in practice is you get a confident prior that's wrong when you have misspecification. But the key thing to note here is that increasing the number of features doesn't require any significant additional work. It just requires a few more inner products to be done. We don't need to do any more system solves, don't need to solve any more differential equations. So we can post hoc, once we've done all our simulation, we can play around with a number of features as much as we like, assuming we have the memory to store the solutions. Okay. And again, this is a kind of pointless part, but just to illustrate what happens if we're doing MCMC here. So if we just take 10 basis vectors, even in very simple cases, we're still typically going to require thousands of iterations of MCMC, even in the best kind of case scenario. Okay, and as the number of features increases in MCMC, we will typically require more iterations. So there are definitely scenarios where MCMC will work faster than this approach, but if you have a reasonable amount of data, we're going to beat MCMC most of the time. Okay. So back to our original problem, we can do the same thing with a PDE. Okay, so this is our original linear operator, our advection diffusion reaction equation. And what we wanted to do was solve this system driven by some forcing that's our Gaussian process on some spatial temporal domain. Okay, and we're going to model our unknown forcing, our unknown pollution terms as Gaussian processes that are vary in space and time. Okay, and the data our sensors give us are typically kind of time averages. So the sensors actually give us very finely temporally spaced data. I think it's every minute or something like that. But we don't trust the data at the resolution, so we tend to average it over an hour because they're low quality data. So we're going to assume we have data that are time averages at different locations around the city. Okay. So the adjoint operator looks much like the forward operator. We just changed some of the signs from negatives to positives. That's essentially all that's changed, as in the other example. But as before, we change our initial conditions to final conditions. We need to solve the adjoint system backwards. And so what we're going to do is, instead of solving the original forward system, we're going to set up these n adjoint systems, where n is the number of data points, where each adjoint system is defined by being forced by one observation sensor. Okay. Yeah, initial conditions become final conditions. And so essentially the work involved here is minimal. This is not a black box method. We need to know about the underlying equations. Okay. But if you can solve your forward model, if you can solve your forward PDE, you can solve the adjoint systems pretty much. They're the same level of difficulty to solve, with the caveat that these HI are often like spikes. You're picking out a small region of time and space. And so you have to be more careful in your solver to, if you're using automatic time stepping, all these kind of things, you can overlook where these sensors are. So that's some difficulty we've not really thought about. But we're doing everything by kind of finite differences, so we can control all of this ourselves. But if you're using a fancy piece of software to solve your PDE, you need some care there. But I'm not the person to talk about that. And the other thing to note is that the cost of solving the adjoint is approximately the same as solving the forward system. Okay. So again, just some results to kind of show it works here. What we've assumed, we've either got 4 sensors, so this is just synthetic data, okay. 4 sensors or 16 sensors. We generate a forcing, an air pollution source that varies in space and in time, okay. And what we try and do, so this is a snapshot at time 5 in our simulations, and what we're going to try and do is infer back, so what the answer is. So with 4 sensors, we learn some stuff, yeah, but it's not perfect. With 16 sensors, we get a very good representation of what's happening here. And so I think we've got 16 sensors here with 5 observations each, so 5 hours worth of data, essentially, okay? And all of this just costs us 80 solves of the PDE. Now, there's no need to do MCMC or anything like that. We get this answer, the whole posterior, with uncertainty. So this is the variance of our inferred source terms in these cases. So you can see the variance is smaller around the sensors. It's larger. It's smaller if we have more sensors, more data. Okay, and this problem can become too difficult. We're assuming quite a smooth pollution source here, which is kind of unrealistic, but there's some kind of sense in it if we're averaging in this very crude kind of modeling way that pollution tends to come from the same bits of the city most of the time. And so if we have fairly kind of smooth pollution sources, we can learn quite well. If we have very quickly varying pollution sources, it's essentially impossible, okay, given the type of data we have. We can learn something, but yeah. Okay, so you can look at the paper for all the results and that kind of thing. Okay. So one thing we're only just dealing with now is how we deal with additional parameters. Everything we've said so far is inferring the posterior distribution for this forcing term F, given the GP length scales, given diffusion parameters for our PD and so on. So we've got a variety of choices we could do. We've done something very naive. We've just got our cost function, we're minimizing the cost function. So, and we're doing it by Bayesian optimization, essentially. Okay? But there's lots of information to help us do that. And if we use the adjoint sensitivities, we get derivative information about this cost function. So we can build that in and so on. We could get a variational posterior quite easily, or we could, if we wanted, embed it in an MCMC scheme, but it doesn't seem sensible. Okay. Just to talk about what happens as your problem grows, okay, this is the linear model we had to solve. Just to reiterate what I said before, if we have more, so this is number of data points is the number of rows, number of features, number of basis vectors is the number of columns here. So to add more features, we just add more columns to this matrix, okay? And that doesn't require any more computation. I mean, we've got a linear model to solve, but we know how to do that very well, even in big problems. Okay. To add data points, we just add rows down here. So this is a kind of embarrassingly sequential method. We don't need to do anything new. As we get more and more data, we just add rows here and resolve a linear model. So it's easy in that sense to extend the problem to additional data points. Okay, so just talk about costs, and then I'll finish. Here, if we just want to learn F, the cost of this is equal to the number of data points we have. We have to do, if we have n data points, we have to do n solves of our system. Okay. Essentially, if you've got a complex model, insensitive to the number of basis functions, so you can use as many as you like. Okay, it doesn't really, I mean, there is a changing cost, but not compared to solving PDEs. Okay, but the downside is we have to deal with the other parameters, non-linear parameters, in some other kind of way of doing things. So, like I say, we just minimize them here, minimize the cost function, but we don't get a full posterior. MCMC, in contrast, will infer all the parameters together, in theory, if you can get it working. And we saw Sally's talk how it would be difficult to do that sometimes. And it's hard to say in advance what the cost is going to be. Yeah? We know the cost, even in an idealized situation, scales with the number of parameters you're trying to infer quite poorly. Okay? Even if you're using HMC, something very efficient, we know there's a cost that grows with a number of features, essentially. And every time you get more data, you've got to kind of run some more iterations of your MCMC scheme. Okay. Okay, so Mauricio can talk about it, so you can look at if you might be talking about the Green's function approach to latent force models, alternative approach. So I'll skip this. It's in our paper if you want to look at it. But the basic kind of conclusion is, if you know a Green's function for your system, that's going to be more efficient than this approach. Yeah. But typically we don't know Green's functions in lots of situations. If you've got a varying diffusion tensor, it's hard to work out the Green's function. If you have to estimate your diffusion, Green's function, it's difficult. And this kind of Green's function approach, you need to work out these covariance integrals, which normally you have to, in many cases, you have to approximate numerically. Okay, so there's some sort of, there's situations where this would be a better approach, Green's function, but the more complex your situation is, the more likely it is that this adjoint approach is going to be a much easier approach. It doesn't require any mathematics on your part, just the ability to solve an adjoint system. Okay, so I think I've said most of the points. Just to kind of say, this is an intrusive method. It does require some work, but fairly minimal work in some sense. You don't have to spend a long time fiddling around, getting an MCMC scheme to converge, tuning it. You just need to be able to solve this adjoint system. The cost grows with the number of data points. So if you have millions of data points, this is not likely to be a winning approach. But if you have hundreds or thousands of data points, it most likely might be a cost-effective way of doing things. And of course, we haven't talked about it here, but there's lots of efficiencies that we could do. So multi-level approaches, more clever use of the adjoint systems, because we can solve them all back in time to where the first observation is and reuse those simulations for the next set as we go back to the different observation operators. So we can reuse much of the simulation information, okay? Gradient-based information, etc. Okay, so that's everything I want to say. So thank you for listening.
Thank you, Rich. Great talk. Any questions for Rich? Maybe I can start with a quick question. Oh, sorry. Was that Omar?
Nice talk, Richard. Question about when you say you need n adjoint calculations, you're assuming you're building the Hessian exactly. You're doing it from the data side. You could do it from the parameter side, but as you argued, you have many more parameters. So in many cases, you can the Hessian admits a low rank approximation, and you can get away with fewer than n. It depends how much information loss there is. But your n here is the number of sensors, but then you also have this time component. So are you assuming that you're integrating, that you have an integral value of the observations over the entire time?
No, so n is not the number of sensors, it was the number of data points. Oh, so sensors times the number of times we did. Yeah, okay. Yeah. So
in that case, I would say that the Hessian is much lower rank than what you have. And so you could do randomized eigensolver or Langshos or something. And then every Hessian vector product would require, a forward and adjoint, and you can probably get away with fewer than and I have a picture.
Yeah.
I can send
no, that's great. Thank you. I mean, I'd love to talk, more with you more about that actually. So we haven't started to explore really these different efficiencies. So something that would be really interesting to look at.
I mean, you have to then invert the Hessian to get the posterior covariance, but then once it's low rank, then you can use Sherman-Morrison. It's low rank plus you have the prior, and anyway, there's some tricks that can be done. The other question was the velocity. You would presumably get that from a local mesoscale weather model.
That's right.
Like that. But that will come in with some uncertainty. So presumably you could treat that as a random field and then marginalize that out, and then that could lead to very interesting.
Yeah, I mean, I kind of philosophy. We know this model is a really poor approximation of what's happening because we're ignoring all kinds of things, and so we're just assuming at the moment a fixed wind speed at a given time point across the city and estimating that or taking it from the weather predictions. But yeah, doing something more interesting there is an ambition.
Joint inference or something.
Yeah, that'd be really interesting. Yeah.
Okay.
Thanks.
Catherine, just bear with me while I try and work out how to get through.
Can you hear me?
I can hear you.
Very predictable question.
So earlier in the week, there was some discussion about how your choice of numerical scheme affects your inference, and and your posteriors. I was just wondering, I think you mentioned that you use a sort of a finite difference scheme with some time stepping. Did you see any effects of that on your pictures at the end?
We've not looked, or rather, I don't know if we've looked. So I'm sure there probably is some effect, but we haven't looked in detail at that, I have to admit. I'm sure that'd be the case. Given.
Related to the question about whether the wind field was time dependent or not, but also I was just wondering about the time, the physics in time, that here, you know, in this location that you're looking at specifically, the sources of pollution are in some sense predictable, like the sort of, it's not the other application which would be trying to locate the source of something bad that's been released, you know, like from a terrorism point of view or something like that. These are coming from factories and things like this, and the time scales of the release are not short. They're sort of in time. It's not like you've really got to resolve things in time if you, these are sort of more over.
Yeah. So you know, we've not done this in detail. No. I know for the city, we've got some toy. Well, it's real data from a point source where they've collected data at you know, very controlled things under controlled situations, and we can look at simple experiments like that to see how well we do. But in honesty, when we do this on the city, the answer we get is not very easy to interpret. We know that the answer we get, if we then forward predict the pollution, has improved our predictions, but it's not really clear whether it's telling us much about the actual pollution. Okay, whether it will do when we build in more careful information and in the kind of way you say, or when we know things about the city, it's a hope. But at the moment, it's essentially just improving our predictions substantially, but it's not really telling us a lot about the source.
Okay, well, one final question then.
I'm going to ask a bit of a speculative question. Well, maybe it'll require a speculative answer, but assuming that you are 100% wildly successful, to what extent do you think this scales so that politicians, people who want to see this model, the council, whatever city you're, do you think this will eventually could run fast enough that they can make real-time decisions on this, right? So say the wind patterns change and all of a sudden, you know, they need some information that the pollution now is going to trick red everywhere. So maybe they say, go inside. Do you think you have that, potentially have that type of scaling in your methods?
Yeah, absolutely. It's not hugely expensive. You know, the way we're solving this system and this small thing, it's minutes worth of computation. If we have hourly data, that's absolutely fine to scale. And so that is our hope. And in some sense, we think this method is likely to be more successful if we zoom out. Instead of looking at Kampala, look at satellite data across a wider part of Uganda or even a wider part of Africa. So yeah, absolutely, it runs quick enough to do that, as long as you have sufficient compute to be able to do a simulation every time you have a data point, which with hourly data we do. So yeah, that would be the hope.
Fantastic. Let's thank Rich again for his talk. So for our second speaker today, I'm delighted to introduce Mauricio Alvarez from the University of Manchester. Mauricio is in the School of Computing, but actually he's one of these trilingual people that can speak languages of mathematics, statistics, machine learning. It's a great pleasure to be able to invite him to speak at the workshop today. Wish I knew what I was doing with microphones.
Hello.
Okay.
Yeah. Thank you, Chris. That's a very kind introduction, actually. Yeah. So I'm going to talk about this idea of putting some physics into Gaussian processes, and I just realized that I didn't have any intro slides to Gaussian processes. That's good that Rich already did that for me. Thank you. Yeah. So this is something we have been thinking about for a while, and is how do we bridge the gap between sort of data-driven approaches, well, actually to machine learning and mechanistic modeling. And we have worked on this approach that we call latent force models. So, so these first two sections are sort of very old, sort of work I did 10 years ago or so, and then the third section on advances on latent force models is more recent work on that. So basically, what we want to do is to build. So the most important aspect of a Gaussian process is the function, and we want to do is to build covariance functions that have some inspiration on physics. Associated with differential operators and covariance functions associated with latent functions. So back in 2009, we called that approach a latent force model. And basically, we can see a latent force model as the Gaussian process with a covariance function that is inspired by a differential operator. So the original formulation was done for what we call a multi-output GP. So rather than just modeling one stochastic process, you want to model, say, capital D processes. So say that you have capital D processes, as you see there, and then what we say is that each of those processes has this operation. Oh, this is not working, but you can model this as this integral here. So the real D here is indexing the processes. Remember, you have capital D of them. And then you're doing these convolution operations between these Green's functions, GD, or smoothing kernels in general, and then this convolution, then the process FD is also going to be a GP, and then you can work out covariances for those FD processes, or cross covariances between, say, process D and D prime. So you can include more latent GPs, and then get a more general expression as the one that you see here, where you are now adding over capital Q latent processes, and each latent process is sort of acting through a different smoothing kernel, contributing in a different contribution to the output. And then if you assume that those latent processes are independent Gaussian processes, then you can work out a covariance function as well for the FD prime processes. So this is a simple representation of this construction where you have your latent process UX, and then you convolve that with these Green's functions or smoothing kernels, and then you get a representation for each of your outputs, in this case, 2 outputs. So each of these Green's functions will be specific to the output that you are modeling. For these joint processes, so you can compute, or you can express this covariance, and this is the equation for that. Processes U are independent, basically, and then this is the expression that you will need to get for specific forms of G and specific forms of the covariances of this latent process. So once again, this KQ here refers to the covariance function of the latent process, UQ, right? So now, if you're able to build this covariance function, then you can use all the machinery that already works quite well for Gaussian processes. Yeah, so you can do predictions of, say, for example, if you only have data for one of the outputs, then you can condition on that data. Or you can also compute cross covariances, say, between the input U, like in this expression, covariance between FD and U. Talking about before, Rich was talking about the trying to find the sources. Then if you have data for your output F, then condition on F, try to do the conditional probability of U given F. So there are a lot of things, practical applications that you could do with these constructions once you have them. So now in the context of these dynamical systems, these G functions actually going to have a relationship to either a differential equation or a partial differential equation. So say, for example, that the outputs that you are modeling are the results of different dynamical systems that being excited by a set of latent processes, as you see here. So you have this, in this case, this ODE of order M acting over the process of T, and that's being excited by this weighted sum of latent processes EUQ. And then for these linear systems, then you can find a corresponding Green's function to that differential operator. For this, then the solution is in the plane of a convolution. Yeah. So the difference with what we had before is that now we are attaching a physical meaning to these functions G. Yeah. So before it was just you just needed the function to have to be a square integrable, but here is these functions G actually associated to say ordinary differential operators or partial differential operators. And then the covariance function that you get, assuming that you also have this independent Gaussian process in the latent domain, then is again this double integral that you had before. Now I have replaced the general input X and Z with the time domain T minus tau, T prime minus tau prime. But then still you have to solve this double integration where again, remember that this KQ is the covariance function of your latent GP. Okay. Right. So this is the general motivation behind latent force models. Is you include some sort of physics into your covariance function of a GP, and then you just use the standard machinery of Gaussian processes to do regression, well, supervised learning or unsupervised learning. Another work that we did was actually putting together several of these Gaussian processes sequentially, and we call that a Swiss latent force model. So you can imagine well, the problem that we wanted to address was like given a multivariate time series, how can we actually segment that series into intervals that have a physical meaning? So this is the latent force model for the section I was describing before. Say for a second order differential equation, you have your force here, which is represented by a Gaussian process with covariance KT, T prime. And then that goes through this system, and then you get your output, which is going to be another Gaussian process with a very specific type of covariance function. So say, for example, if you sample from your force, and then you act with that sample through the ODE, then you get this kind of output. Yeah. So it's interesting because then you see there is some dynamics going on. Yeah. So there is some, for example, inertia happening, because obviously you have this dynamical system. Now this extension of the latent force model I was looking at was to what happens, application based in robotics I'm going to talk about later. What we want to do is that there are specific intervals where these parameters are going to be changing. Yeah. And what we would like to do is to actually automatically find those intervals where there is a single dynamical system representing what we observe. So say that you have these 3 intervals, and each of the intervals has different forces, like this one here, which is changing, or these ones which are more constant. And then each of those forces are going to be generating a particular output. But what you observe in sort of an unsupervised fashion is just a single time series. Yeah. So if you're given this time series, can you actually use this type of construction to get the individual forces and the individual systems that represent or are sort of describing these intervals? And then the other thing that you would like to do is to actually find the points in which this switching regimes happen. So maybe it's a good time to talk about the application. So the application we're looking at is this humanoid robotics, and there was a lot of work 10 years ago or so, where people were looking at identifying from a multivariate time course series what they call motor primitives. So if I have a high dimensional multivariate time series, what I want to do is to find a specific intervals in that time series that represent them by primitives of motion. And if you can sort of segment those motion primitives, then you can compose them to generate more complex motions. Yeah, so that was sort of the rationale to try to find a model that is able to identify the specific primitives in the multivariate time series. So because we're working with dynamical systems, one of the things that is really important is that there is continuity between this each interval. Yeah, because you're working with a robotic system, you wouldn't like that robotic system to do abrupt motions. So something that we were not doing before in the previous formulation was to take into account the initial conditions for the differential equation. And that's something that we actually exploit here to be able to bring that continuity. So what we formulate in this model is a set of restrictions that tell us that the values of the, say, position and the velocity for one of the sort of the degrees of freedom of the robotic arm, they need to be the m values of those for a particular interval, they need to be the same initial values for the next interval. Yeah, and that kind of restriction is to be built into the covariance function of the Gaussian process. All right, so this is just a plot of 3 those intervals. So these dashed lines here are the switching points. And then these are samples from 4 outputs, different processes going on. And you see that even though the switching point, for example, is here in 1, the change doesn't happen straight away because these are dynamical systems. So the change in dynamics is happening, few time points later. One thing we did was to test this because this is an unsupervised learning model. We really don't have a ground truth of what is the truth number of sort of motor primitives. But if we repeat this, do this exercise several times, the expectation is that you can recover at least the same number of motor primitives. So what this real world example is showing is precisely that. So if we use the marginal likelihood as the criteria to find the number of motor primitives in 2 repetitions of the same exercise, which is plain table tennis before, then we would expect that at least we get or recover the same number of motor primitives. Okay. Right, so what I'm going to talk about is more recent work we have done on these types of models. And this work was done by my previous PhD student, Christian Guarnizo. So the main problem that we have when we work with this covariance function is that if you have a simple, even if you have simple ODE, then you need to work out the analytic expression for your covariance. Yeah, so we can do this, but the expression that you get will involve, for example, error complex functions. And I remember coding this back in the day. You need, like, for this to run efficiently, you would have to do, C or Fortran, which is not bad, but it has another level of complexity. So one thing that you could do is to actually represent the latent covariance of your latent GP using Wagner theorem. And then when you use Wagner theorem, you get this representation for your covariance. And basically what I'm pointing at is if you use a Fourier feature representation for your covariance, then you're able to uncouple these two integrals and just have a sort of vector representation, a basis vector representation for your covariance function. And this is what we did there. So if we go from this expression here, and we reorganize these terms, so as you see it in the terms with tau, the terms with tau prime, then we get this form of the covariance, where these VD now are just the Green's function acting now over just a complex exponential. And we just call that the random Fourier response feature. So now you have a covariance function where you have a new type of features, and those features basically are transformations through dynamical systems of the original features that you use to construct the latent GP. And then we represent, to solve this integration, we do the same that the original authors of the random Fourier feature paper did, which is just sampling from this integral to be able to approximate the covariance function. So what I'm showing now here is the computation of this covariance matrix for two outputs. So you have output 1 and 2. One is overdamped. This is a second order, two systems. One is overdamped and the other is underdamped. And then here is the full covariance for the exact ODE2. So it's solving the two integrals that I showed you before exactly analytically. And this one is the approximation using just 100 features. So we use this Frobenius norm. Perhaps it's should have used another norm. But the thing is that when you increase the number of features as expected, these to start to appear very, very similar. And computing this one is much faster than computing this one. And because it's a representation of the covariance in terms of basis functions, then it opens the door to do many more algorithms that are based on basis functions. Another extension that we did recently was a deep version of these models. So you may be familiar with something called deep Gaussian processes. So the idea of the deep Gaussian process is that you sample from these GPs, and then the outputs of those GPs you use as inputs to a second layer of GPs, and so on and so forth. So basically you're composing, doing composition of GPs. So there was this work by Kutahar where they did the representation of the covariance functions of those GPs in the deep GP using Fourier features. So basically you end up with something that looks very similar to a Bayesian neural network. And then the extra bit that we did was to, rather than just using the normal features that the deep GP with random Fourier approximations would use, we changed those features with features that actually have a more sort of physical meaning or intuition. And this was a work that done by my PhD student, Tom. So here we have this, I think it's called the Charis data set. Is a FissioNet data set where you have these three outputs. And then the experiment that we're trying to do is that you give us data up to some point, then how would these models extrapolate out of the some of the training data? So just want to focus perhaps on the top one. So the training data goes up until here, and then we're trying to do the extrapolation, doing a deep Gaussian process, and then doing one of these deep latent force models. And you see that the answer, the response is quite better there. And then I think the reason is I mean, like all these covariances that we use implicitly in this construction, actually based on these Fourier features that have more this take into account this oscillatory behavior that is more sort of clear here, whereas that for the DGP is difficult to pick. Right. The other extension that we did for these models was to go outside the linear assumption to the nonlinear regime. So there is this extension of this convolution. It's called nonlinear convolution. This is based on something called the Volterra series, which is actually well known in electrical engineering. The idea is that you can represent nonlinear systems, at least some kind of weak nonlinearities, using this construction that you see here. The actual construction uses C going to infinity. You call this the truncated Volterra series. Now, again, you have this kernel here, which is called the Volterra kernel. And then if you assume that this U is a latent Gaussian process, then contrary to what we had before, you can't really compute, well, assume that this is a nonlinear thing. So this is not going to be a GP anymore. But what we could do is to approximate this output process as a Gaussian process just by using the first moment and the second moment, I mean, the mean function and the covariance function. And that's what we did. So we have this F tilde G, and then now we can compute this mean process and we can compute this covariance function. And there is a formula that you can use to compute this in a sort of have an analytical expression for the mean function and the covariance function for this model. And that is interesting how you program this, because the form of that form of the covariance or the mean is going to change depending on the value at which you truncate the Volterra series. So this is work that we did with Will, who's a postdoc, and Christian again. So what we're showing here is, this is a synthetic example where we created these two outputs with these simple nonlinearities. So the input is this dashed line that you see here is just a very simple input. And then here we have like a threshold function that says if the input is positive, then the output is just this is a constant here. And then if it is negative, it's a minus constant. And the second output is sort of like a rectified linear unit. If the input is positive, then you keep the same. If the input is negative, then is zero. So what you see here as red dots are just the training data. And then each of the columns is showing the prediction that you get with this model and the uncertainty that you get. So C equals 1 would be like just the GP, yeah? So we know the GP won't be able to approximate this very well because of the smoothness. So you can't really approximate this data well. But as you start increasing this value of the Volterra series 5, then you start getting a very representation of those nonlinearities. Any question? Right, and the last vignette I want to talk about is this non-parametric latent force model. So in all these models, I assume that I know the Green's function. But what happens if I don't know the Green's function? I would like to have some way to approximate that. So basically what we do is, well, we build this model on top of something that was published previously, where this convolution here assumes that you put a Gaussian process both on the smoothing kernel and on the latent GP. But for the latent GP, they used, well, they assumed that we just a Y noise process, and this G, well, is going to be the GP. It's going to be a GP. So what we did in this paper was to extend this framework to the one that uses the Volterra series. So what we do is that we put a GP on each of the Volterra kernels, And also our latent GP is sort of a smoother GP. So it's going to be a GP with a different covariance function. And changing as well, the other thing that we did in this work was to change the inference approach based on functional sampling and the Mathenon rule. So this was work by Magnus and Mike. So what we're showing here is that this is sort of similar to the first picture that I showed you, where we have a latent process. Yeah, that latent process follows a GP. And then instead of assuming a fixed form for the Green's functions, we have another GP for those Green's functions. If we do these convolutions, then we get this representation for the output. And that would be like a linear model with a non-parametric representation for G. Now, the nonlinearity comes from including these additional terms in the Volterra series. So for example, now here we included the second term in the Volterra series, and you have this process where these U's are GPs and these GD are GPs as well. So you have this representation that you see here. Because of you're doing this, you only care about the diagonal of these operations. And then you get these representations for the outputs. And then what you get then at the end for your outputs is going to be the sum of these processes. So this is a toy example. We were constructed this very nonlinear process going on here, and we're looking at how these different models are able to predict this extreme behavior. And some of these models that use the Volterra series, so this GPCM model is the one that was proposed originally, where it just assumes that the latent GP is a white noise. And then these other models here, and these models are able to actually represent quite well that extreme behavior. And this is a typical example they use in control. Maybe some of you are familiar with this. It's called the cascaded tanks. So you have these two tanks, and then the top tank is using this pump to get out water from a reservoir. And then it drains the water to a lower tank. And then the data that we have, this is sort of well-known data set. You have one input, which is the voltage in the pump, and then the output is the volume of the second tank, the one on the bottom. So you're giving two instantiations of that data. So you have one time series for the input and one time series for the output. And then the challenge is, if you are given only the input for the second replica, then can you predict the output? So we extended the model of the Volterra series to actually allow for specifications of the input U. And what we're seeing here, this is the test data. So first the bottom. So this is the prediction that we do. The solid green line is the mean prediction. And then this dashed line is the actual real test data. So it's actually doing not bad. And what we see here, the best model that we used for this was the one that used 3 terms in the Volterra series. And these are the forms of the Green's functions that were learned for that third order filter or third order Volterra series. Right, and this is sort of more like some thoughts about this. So usually we have all this sort of a spectrum of things where we, on one side, we have this white box modeling where we have a very detailed description of a dynamical system or a spatio-temporal system. We call that white box modeling. On the other side, we have this black box modeling where we don't have any idea about the physics, but we just put a data-driven model. And then what we had, well, things I've been thinking of is how do you actually, what is in between these things, yeah? And how do we build models between these two things? And there was this nice paper by Bernard Sholkov and other people talking about the relationships between these and you know, machine learning and AI. So talk about this physics-based modeling or statistical modeling for this black box modeling that we know is these models are data hungry. The physics-based models are better representation of what happened, but we don't know when we have a complex systems, it's difficult to fit them. Causal models have attracted a lot of attention. Where do they sit here? Yeah, you have a causal model going from this side of the spectrum to this other side of the spectrum, for example. Or are there some sort of latent variables that we can use to actually say what does it mean for a model to be physics-based or data-driven based? Is there some levers that we can plug here so that we can move better to this side of the spectrum or that side of the spectrum? Right, so I'm gonna finish there. So yeah, so these latent force models incorporate dynamical systems into a kernel function. I didn't talk about the PDEs, but we have done work on PDEs as well, particularly in computational biology in Drosophila. Random Fourier features allows us to compute these covariances very fast. We introduced this Volterra series coupled with the idea of having a latent GP for nonlinear systems. And then we have some initial experiments showing that you could do non-parametric versions of these models. I think that's it. That's some time for lunch.
Well, questions. You're gonna get to the questions. Any questions for us? Yeah. Okay, please.
Thank you for the talk, very interesting.
So regarding the Volterra kernels approach, this is new for me. I mean, your approach, I'm aware of the Volterra approach and so on. But how does this C coefficient play a role here, the truncation index? You showed some results with 1, 2, 3, or 4 truncation index, but I couldn't see much difference.
Probably for
this didn't make
much difference.
But in general, can you comment on this? And in my experience,
We
are looking at more deterministic approaches, and then it gets very
involved and tedious to deal the estimation and yeah.
Was this
Clear or?
Yeah. I think that's an important question and it's a difficult one. Yeah. So in the experiments that we look at with 3 terms, 4 terms was already enough. Yeah, because the contribution of those terms over that is very small. But I think it will depend on the application. Yeah.
You mentioned you are looking at weakly nonlinear, or you take into account weakly nonlinearity.
Yeah.
Which means that after some level, you can just ignore the.
Yeah.
Which you had a question?
Thanks. So one of the things we often want to do, we know something about the system behaves, some of the differential equations, but we've seen part of it's kind of missing. So we might add a Gaussian process, say, on the missing derivatives or whatever, the missing states. So if you've got this Green's function formation, if you know part of the structure, is that easy to deal with? Is the Green's function for the whole system the bit you know plus a bit, or does that not drop out in that kind of way?
That's actually interesting. I haven't thought about that. Yeah, I don't know. There might be ways in which you can do a mixed model or something with the bit that you know and the one that you don't. But yeah, I haven't come across it. Yeah.
Did I understand correctly? You have to solve the differential equation once for every Fourier feature.
You don't. No. The only thing for the Fourier feature approach, this is where you need to solve. This is the thing that you need to solve. Where G could be the Green's function of the differential equation.
Right, but integrating against the Green's function once, isn't that the same as solving the differential equation?
Well, yeah.
Okay, so is it true that the number of times you have to do this scales with the number of Fourier features that you have, or is that not?
once you have the expression, that's it. Yeah, you just use the expression to compute.
Oh, so you do this like analytically?
Yes, you do analytically. Yeah.
Okay,
Yeah.
that's interesting. So that, yeah, so that limits to an extent the kind of dynamics that you can handle.
Yes. So in these original models, the G was usually associated to a first order, second order differential equation. But that was one of the reasons we wanted to do the non-parametric bit. But because solving these using symbolic programs is kind of a way to move forward. You can potentially do this automatically using symbolic solvers. And that's something we're working on at the moment. Yeah.
And if that works, then everything else is for free, essentially.
Exactly. Yeah. Yeah.
Any further questions?
Sorry. So if I understand it correctly, so you trying to model the input-output behavior of a dynamical system, right? So some input, the U, and then what is the reaction of the system, right?
Not always, but you could do, yeah.
I mean, the Green's function is a bit like this, right? Or,
yeah, but I think we're more motivated for including physics into these covariance functions. Yeah.
sure. But
Because
I was more thinking about the Volterra things.
Yeah.
So that's a generalization of transfer functions, essentially, right? Of that
yeah, yeah, they're quite related, yeah.
And so you're assuming stationarity there? I mean, the system is also in stationary. I mean, it's all translation invariant, right? In time or so?
Yeah, yeah.
Okay.
Yeah.
Is that sort of realistic in nonlinear systems that they're sort of in a stationary regime?
No, I don't think so, no.
Right. Okay,
Yeah.
so you would need to recompute one.
Exactly, yeah, yeah, yeah.
Okay, right, thank you.
Right, let's thank Mauricio once again for his talk.
Thank you.
Right, welcome back, everybody. Hope everyone had a nice lunch. We have 3 talks left in the workshop, and save 3 of the best speakers till last. So first up, we've got Steve Niederer from King's College. So Steve is a co-director of the newly formed Turing Research and Innovation Cluster for digital twins. So Steve is actually going to be able to illuminate us as to what is a digital twin, in addition to talking about computational cardiology. Thanks, Steve.
Okay, so I thought I would take a change of pace and try and reduce the number of equations and talk about digital twins. So we'll see how we go. So this is just to acknowledge the research group. We work in a somewhat different environment from many people possibly here. So we work inside of a hospital. So we have our research MRI and a research cath lab or surgical space. And we're all sitting around the offices in St. Thomas's Hospital, which is down in central London, opposite Big Ben. And we have our PhD students and the postdocs and our clinical fellows who are doing the research studies and our alumni. So these are the people who've done all of the work. So Marina, who's sitting at the back, will be the person who I'll be pointing to answer most of the technical questions. So what we have here is why we need digital twins for patients. And one of the reasons that we're interested in is because there are many, particularly in the case of cardiovascular diseases, is we treat all patients the same and we get very different results. So this was a study where they took patients who had heart failure, they've been treated, they've recovered from their heart failure, and they withdrew their medication to see what would happen. And 40% of them had their heart failure relapse. So that was not great. And the conclusion was that if you have recovered from heart failure and you're taking medication, you should keep taking your medication. 60% of the patients, though, didn't relapse. And those patients are going to continue taking the medication under the current guidelines. And so these are people who possibly would not have the side effects, not have the risks associated with medication, but are going to keep taking it because that's what the guidelines suggest. We can also look at people who have just started their heart failure medication. And for those patients, about 30% of them are going to get better after a year, whereas 70% of them are not going to improve. And so are they getting the right medication? And we also have pacing therapies, which we deliver. They cost 15,000, 20,000 pounds per person. They have a lifetime implanted device, lifetime risks and complications. And about 20 to 40% of those people don't benefit from their therapy either. So we have a large number of therapies we're giving people based on guidelines, which are based on population data, and it's not always going to be best for every single patient. And what we're trying to do is effectively have a better understanding of our individual patients from the information that's available. And the information is always incomplete, that we don't have a full picture, we can't make full measurements, that information's noisy, it's not collected in the best system, what have you. And our kind of thought is that we can use physics and physiology to fill in the gaps, to kind of make a representation of that individual, which is not perfect, it's a caricature, but it does at least give us kind of a way of integrating all the information we have to make a full description of those individual patients. And the goal here is then to move away from an idea where instead of measuring cardiac function and using that for diagnosis, that we'll have a better way of understanding the underlying causes of that individual patient's pathology, and then we can treat based on the mechanisms of the disease, not on their kind of emergent behavior. This is the idea, but we will see how we go. And so the idea that we have for kind of implementing this or delivering this type there is the idea of a patient digital twin or the cardiac digital twin. And we can spend the rest of this meeting talking about our definitions, which is what a lot of digital twin meetings break down to. But our perception is that for a patient digital twin, you'll have a patient, you'll have some healthcare system where they'll be taking measurements. You will have potentially wearables that will also be giving them observations about this individual. These two systems ideally will be linked together, but currently could be more linked. We will have our physics and physiology mathematical representation of that individual patient. And this effectively becomes our digital twin. We'll be able to link that in to get data from wearables. We'll have population priors to constrain this or add in information which we don't have. And then if we think about what we can use this for, it's for improving monitoring of those patients. So we have a better understanding of how they are at any time, doing forecasts, doing what-if testing, and giving us some insight into the mechanisms which are driving their disease. If we have more than one digital twin, though, that's another interesting aspect where we have a digital twin of one patient, and in hospitals, there are lots of people. And so we might have some observed trajectory for this patient, and then we will have a forecast patient trajectory, but then we might have a large number of other patients who also we have digital twins for, with also an observed trajectory, also with forecasts. And there's a question that we have as well, which is how do we better network these digital twins together to be able to share information between those digital twins as a population to accelerate the or reduce the costs of calibrating and doing forecasts for each marginal patient that we might recruit into our network. So this is the idea, and this is what the funding grants look like. And what we're doing at the moment is really taking our patient and our hospital data and trying to calibrate these models. And that's about where we're up to. And it could be better, but this is the framework that we're at. So what do our models look like? We start off with a model representing the electrical physiology of the heart. So with each heartbeat, there's an electrical activation that starts in the right atrium, which is one of the top chambers of your heart, propagates over to the left atrium, and then activates the two main chambers at the bottom. The electrical signal at the whole heart level is due to a series of proteins which span cell membranes. So all of the cells that make up your heart have proteins which span the membranes, allowing ions to move in and out of those cells, and that's what gives the electrical signal. That electrical signal is moved into a chemical signal by the release of calcium ions from stores inside of your cell. Those calcium ions bind to another set of proteins, and those proteins are the sarcomere, which cause the regulation of contraction. These cells are embedded inside a tissue matrix, and that gives a preferred orientation for the electrical activation and for the stiffness. We can combine that with geometric representations of the heart, then give us a description of the mechanics to get that heart to pump. And if you spend enough time in a computer science department, someone always wants to do CFD, and so you can then start doing blood flow. So this is representation of the system that we have, or the modeling framework we have for representing the patient's heart. And it's put together through an absolute portfolio or plethora of software, from my group software CMerge to CARP, which is our simulator, and then a whole series of machine learning and visualization tools on top of that. So what we'd like to do with these models is we'd like to make some observation. This is supposed to represent the volume and pressure of the heart. These are two characteristic and mechanical functions, and be able to identify what are the mechanisms, so the proteins in the cell, which are going to be causing the disease. So we'd like to say, here's what we see, this is the problem. And what we don't get from our models is that. What we get is that you can propose a problem at the cellular level. So this is the protein that's not working, this is the contraction that's not working. You can then run simulations to test that and compare that to see if that's a plausible explanation of your data. So the models aren't able to tell you what's wrong. They're able to be a framework for testing what is wrong. And the problem is this is very expensive to do. And so the way that we've done that in the past is we send Alda Rinaldi, our friendly cardiologist, into the cath lab, which is a surgical space. They put a wire from the groin up through the aorta into the left ventricle, and they make measures of the pressure in the patient's heart. So these are, it's about 1,000 pounds per tray or per sub. And what we then do is we take our computational model representing in this case, the two ventricles of the heart. We guess the parameters based on prior experience or desperation, make a model. 4,000 CPU hours later, we've simulated the pressure transient. We compare the two, and then if it's close, we accept it and put that in our paper. And if it's not, we repeat this process again. And this was historically how we were going about this. This is in kind of the classical naive engineering sense. So what we wanted to do was see, there we go. What we wanted to do is see if we could use, and I write machine learning, this is very much a marketing exercise, Gaussian process emulators would be a better description, for inferring the mechanism. So we wanted to have a test case. So the test case we have is a rat heart. There's a rat, and this is a control rat. This is an unfortunate rat who wasn't in the control arm, and they've had their aorta restricted. So that is increasing the resistance for blood leaving the heart, and that's going to cause the heart to kind of have a pathological response. And our question was, if we get pressure and volume measurements from these animals, can we identify that this is the problem? So we made a mathematical model of the rat heart. So we had our mathematical model of the cell. We had a mathematical model of the proteins in the cell, which generate force. We could look at this we could do MRIs of rat hearts to get a description of the anatomy. We could do diffusion tensor imaging, where we look at how water molecules move preferentially in different directions to get an idea of what the tissue structure is inside of the rat hearts. And then we can make a nice simulation, which works, which gives us a nice contraction of the rat heart, and it kind of twists around and pumps blood very nicely. So we can have a reasonable go at simulating the rat heart. We then have a series of model parameters, and these are just to say that we have parameters which are for cellular contraction and for boundary conditions, effectively. We want to map those onto a series of outputs, and these is a parametric description of the volume transient and of the pressure transient. So parametric descriptions of the mechanics of the heart. So there's a isovolumetric relaxation time and end diastolic volume and peak pressure. So numbers that doctors might be interested in, but we can just take those as a series of scalars. And we have our framework, which will take these 8 input parameters, have a physics-based simulation to generate the mechanics, post-processing generate the pressure and volume curve, and generate 14 different output parameters. And on a single core CPU, this takes about 4 hours to compute. So we would then train our Gaussian process emulator to 1.2 seconds and get a 12,000-fold speed up, which is not a surprise to anyone here, but these are the slides I give to everyone. And so we can then do sensitivity analysis on our sham animals and our disease animals. And what's interesting for us for sensitivity analysis was that one of the people who were interested in this project was Pfizer. So Pfizer, or do they need to look at using diseased animals when evaluating a particular drug that might act on a protein and have a particular output that's measured on? And so if the sensitivity, in this case, the calcium sensitivity, if your drug was acting on calcium sensitivity and you were trying to improve this measure end diastolic volume, then a control animal might not be the best one to work on, because in the disease case, this tissue stiffness is having a much bigger impact on that output variable. So this was a way that from the drug company's perspective, they could compare to see if their drug target that they were looking at was very important in the control versus the disease model, because that's going to inform which type of animal you can use. And then we can look at calibration, and after calibration, again, 4 million evaluations through calibration, which we did with Bayesian history matching. And we could see that Z, which was the aortic resistance, was much higher in the aortic banded animals and the sham. This kind of gives us some confidence that we're able to identify that we can use the models to identify where there is that increased resistance and the aorta or the pipe coming out of the heart, confirming that we're able to identify the pathological cause that would apply to that animal, we can identify through the simulations. So this was a nice test for us. And the heart is complicated. It has many modes of failures. So it's not like and by that, I mean that if I have a large heart and it doesn't have enough contraction power, it's not going to eject all the blood. And so it's not going to complete a cardiac cycle, and my simulation is going to fail, and that parameter set won't have any values associated with it. And when I then try and train my GPE, that output space is blank. And there are many, 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 many ways, both numerical and physiological, that the heart models fail. And so we end up with holes in our output space. And we deal with that by ignoring them. And possibly, it'd be great if there were other ways to work with that. I'm very happy with Alex's suggestions there. And so about 20 to 30% of our simulations don't run. Or so only 20 to 30% of our simulations complete. So we're running a lot of simulations which aren't working, so it's very inefficient. So as an audience of computational statisticians, these are the problems that we're facing with when trying to use some of these tools, and we're very happy for suggestions on how to improve this. I would say that we did try and just use a simple logic regression to differentiate the spaces between working and not working, and that was not a successful strategy for us, largely because of the multiple modes of failure.
Does that mean like the codes fail? Is that what you did?
Well, there's two ways. So one is that you might take a series of parameters which make your code, your equations much stiffer than they have been. And so your numerical tolerances have now kind of shifted, and numerically it falls over. Other times in a cardiac cycle, the heart has to fill with blood and pump blood, then fill with blood, then pump blood. And if it can't complete that loop, you end up with you can't do the post-processing. So it will start to fill with blood and then never get to a point where it starts to eject blood because the parameter sets have shaken, and that simulation's now failed.
Sometimes PDs are wrong, but sometimes numerical schemes.
Yep, and sometimes you've just selected a point in space which is incompatible with life. And so you don't even want to be point sensitive of that, but it's sometimes hard to differentiate those because it just doesn't work. So these are, again, very happy for ideas.
So you said that you tried logistic regression. Why didn't work?
Because it wasn't accurate enough. So we were throwing away huge numbers of simulations where it did work, and the logic regression said that it wouldn't, or vice versa. And so it's not necessarily a convex space of working and not working. It can be a horribly complex space because there are so many different modes of failure. And sometimes it's a PDE solve, sometimes it's a physiology solve. So it's not obvious. So what we then did, oh, sorry, yes.
Are you already considering the different patients, I mean, different geometries?
That was just two rats.
Okay. So the same.
We're moving on to the different patients now.
Okay.
So when we move on to patients, this is kind of data sets that we get. So this is where we've put a pressure wire, again, one through the groin, one through the venous system, one through the arterial system. We get measurements of pressure in all the 4 different chambers. We get electrical measurements. So we're putting in little electrodes and putting them against the wall of the heart, and we can look at how that heart has been activated. We're getting volume measurements. We're doing CT. So we get a lot of data from these patients, and we collect this particular trial, which we're running. It's going to collect 70 patients with, gigabytes of data per patient. And so how we process that is going to be a challenge. So we then make a model of a human heart, which generates the same type of data. So this is activation patterns, and it's mechanical summaries of measurements coming out of these hearts. And the question is, how do we calibrate these models to the experimental and clinical data that we're getting? So the clinical data is noisy, it's not always consistent, it's not always reliable, and the simulations are all reasonably expensive. And by reasonably expensive, I think it's about 6 hours on 512 cores per sample. So for us, that's not a disaster, but it's about £4 to £5 per simulation, and you get through those pretty quickly when you're doing hundreds of samples. So we have these models, and then these models have multiple layers. So within this model, we will have a model of the cellular electrophysiology of the top chambers. We'll have a model of the ventricular cell properties. We'll have a model of the boundary conditions from the blood supply. We'll have mechanical and electrical tissue properties in the atria and in the ventricles. We'll have differences in different regions of the heart. And we also have boundary conditions with the pericardium, which is the sac, which the whole heart sits in. So we have a ton of different models, and we wanted to know which of the parameters from these different models can we calibrate with the data that we have, or have a feel for that. And so we have about 120 parameters, which is a good enough space. I know everyone was talking about infinite spaces yesterday, but 120 was nearly infinite for us. And we wanted to look at how we could do that sensitivity. So we started by breaking the model down into different parts. So we could look at just the model of the cellular physiology in the ventricle. has 17 pumps, and you have a thing here which represents all the different proteins which are bringing ions into the cell and moving ions around inside the cell. And so we end up with 29 parameters characterizing the density of all of these different proteins and the electrical and the calcium side of things. So we have 29 parameters for this ODE model, which represents the electrophysiology of the cell. And we know that there is a chemical transient that's going to come out of that, which is calcium. And that's the main signal that comes out of our cell for driving contraction, which is what we're looking at. So we can parameterize our cell model into kind of how long it takes to, again, in parametric representation of the curve, how high is it, how long does it take, these type of values. And then we can do a sensitivity analysis on the cell model, looking at all of the different 29 different parameters. And we take a cutoff at the cell model and take the parameters which represent 90% of the sensitivity. And these we can then choose to ignore as we go forward. And we can then do, but then some of the samples that we then generate from these cells are going to generate unphysiological traces. So they're going to be interesting, but the samples are not going to be viable or compatible with life. So this was, again, an idea about how can we improve or enrich our samples so more of them are going to work. So what we're doing there is Bayesian history matching, where we try and reduce the samples at the cell model levels. We'll have our cell model, we'll sample a parameter from that, and then make sure we calibrate that so that it is going to represent a physiologically plausible sample or representation of a cell. So this is GP training, generate test samples from our GPE, evaluate, differentiate to implausible, not implausible, generate more samples, perform more simulations, and then retrain our GPE and kind of go around in this loop. So zooming in our parameter set on the history matching to get a kind of a confined space, which is going to represent the physiologically plausible cell. And this is going to work. We can then do that in multiple waves, repeat this one after the other until we kind of identify the plausible space in red here, which is the samples where we're going to accept those samples when we're doing our sensitivity analysis. And so then we end up with a framework where we start off with our 4-chamber heart model. We have our submodel analysis, so we've broken that down into 5 different parts. Some of those parts were broken down into 2 separate parts again. Each one has a global sensitivity analysis on each subcomponent of the model. We do history matching at different levels to identify physiologically plausible representations of each of these submodels. And then from those kind of set of parameters from each of the submodel GSAs, and then taking plausible ones, we can then perform our global sensitivity analysis on the whole heart. So this was a process of going down from the 120 parameters that we started with in the 4-heart model down to about 45 parameters in the final model that we're looking at. And again, very happy for people who have ideas about how we can do this in a different way or in a more automated way, because this has not been an easy process, and it's been a computationally expensive process. But what you end up with here is a nice grid showing you the sensitivity between all these different indexes or clinically interesting indexes of mechanical function of the heart and a whole load of different proteins on the bottom. And what's nice is that these proteins map onto genetics. And so this kind of provides a way of mapping your potential changes in genetics of particular proteins on the x-axis, and then identifying which indices you might want to measure or where they might affect on the x-axis for mechanical function. So this was something that, or if you see a particular change in mechanical function, you can then come across and say, well, what are the particular proteins that might be having an effect on? What are the potential causes of changes in that particular input? So it's an interesting idea for clinicians as a way of kind of having an understanding and mapping from that whole organ phenotypes down to the cellular phenotypes, as well as providing us some ideas about which of the parameters we're going to be most able to calibrate from this clinical data and the ones which we're really not going to have a good shot at doing. And so this was all done by Marina, who's at the back if people have questions. But again, the heart is complicated. It's multi-scale and complex. So we had to build a full model and then we had to take that whole model apart to do this analysis. And so that makes it a very bespoke, labor-intensive and arduous process. So it's not really a scalable process for different systems. And this was just to point out, this took about 1.3 million core hours to do one heart and on one anatomy. And we're going to get on to the end of this is UK Biobank, where they have 100,000 anatomies. And so how do you reconcile these two things? So the other area, and Chris, you can kind of tell me when I'm completely out of time. Excellent. The other area was looking at shape. So we've looked at one patient and looked at the function of trying to identify, and we've got one anatomy there. And so one of the things we were interested in is how can we start to perform a sensitivity analysis or identify what parameters are important when we think about patients who have different shaped hearts, and can we do sensitivity analysis over shape? So for us, we have a CT set. These are healthy patients. By healthy patients, I mean patients who came into the emergency room with chest pain, had a CT to see if their heart was okay, and it was. They just had indigestion. And so they became our healthy controls. So it's a great way to get data. Build a small cohort of 20 patients. So we've had these high resolution CTs, segmented out all of their hearts, labeled those, made meshes, labeled all those meshes consistently. And we can then look at how we might want to represent these shapes. And so if we wanted to just use the CT images, there's about 1.5 billion values that go into a CT image of a patient's heart. We could do the labeling. That's about 40 million values. We could use the mesh, and that's about 3 million values. Or we can use principal component analysis and make an statistical shape atlas, and that's down to about 10 to 50 values for the weights. And so that makes it a little more tractable to do analysis of these. So we're going to use a statistical shape model to characterize the patient's anatomies. And we can do this here, where we look at the three main modes, and we can look at how they vary. And it's kind of there's a whole community out there who are interested in how shape varies and changes. But for us, it was just a compact way of representing the anatomy. And we can then plot to say how much the variance of the shape is explained by the different modes. So we can go along from 1 to 18, and normally you take about the 90th variance, 90th percentile of the shape variance, and those are the modes you then use to describe the shape, and the rest you say are going to be noise. But although this is variance for explaining these modes and kind of this 90% cutoff, that is variance for explaining the anatomy. But that doesn't mean that those modes corresponds to variance in function. So just because a mode is important for changing the shape of the heart doesn't necessarily mean it's going to be important for changing the function of the heart. And often in these things, we'll do statistical shape analysis, and they'll say mode 14 seems to be really good at predicting patients who are going to have a heart attack or not. And people are like, well, that's hard to say. That's not very important. Look, mode 14. And so we wanted to say, can we determine if some of these higher modes have an impact on function, and can we do that with sensitivity analysis? So for that, what we did was, and this is kind of taking our 18-dimensional space and projecting it down into 2D, we have shape mode 1 and shape mode 2. We can take a series of samples within our shape mode and shape mode 1 and shape mode 2 and use these to generate meshes. We can keep going through this with like a latent hypercube sampling. For each one of these samples, then we can then create a new mathematical model of the patient's heart. We do a simulation of that heart with electrical activation, solving it to beat. We can then take out a series of biomechanical outputs and electrophysiological outputs. We can represent those as a series of kind of phenotypes, so scalar values describing parametric descriptions of these different outputs. And that is then going to give us a map. So we have each one of these different phenotype features is going to be a feature on the y-axis, and we have these sort of modes. And so we can take these down and generate a field of features over that mode space. And that's what we can then use to train our GPE. So we train a GPE which takes in shape mode weights as the input and has the output as being one of these features. And that, again, following a relatively standard procedure, allows us to do our sensitivity analysis and start to look at what effect these different shape modes have on different types of functions. So left ventricular mass, highly dependent on mode 1, which in these problems often describes the size, whereas other features such as the rate of pressure development is highly defined by mode 9. And so that's been defined by a much higher mode, showing that there are some subtleties in the shape variance which don't explain a lot of variance in the shape, but are very important for explaining function. So the next step is also that if we think about adding this in, this is a true for all hearts of all anatomies within that statistical shape atlas. So if we can repeat the process that Marina did on one heart with shape included, it makes you global statements which can be stated over whole patient population groups, which we have not done. So the challenge here, though, is that each sample requires a remeshing and building an entire model from scratch, which is not always easy to do reliably and not always easy to do in an automated way where you can be completely confident that it's going to work. The meshes that you generate might have thinner regions or thicker regions, and so the resolution of your mesh might need to change to represent those. And so the edge length of each of your elements might need to automate. and that we might have very different shapes for healthy and pathological patients. And so you end up with a lot of variation that you're kind of explaining in kind of a hypercube space, whereas you actually only have variation between two different islands of people who are healthy or not healthy. And so that might also lead to misrepresentation of results. So again, very happy for thoughts on how to address any of these problems. Lastly, I want to talk about how we scale this up to more people. And so this is UK Biobank, for people who aren't aware. Many moons ago, the UK decided they were going to scan or kind of characterize about 1 million people. Of those 1 million people, a sub-study of those, it was going to be 100,000, but they're still collecting it. So up to 56,000 people have had cardiac MRIs. And they also have 54,000 people have also had ECGs, which are measurements of the electrical activation of the heart. So this is reasonably sized data, but it's also data which is large enough to start thinking about genetics. So it provides a way of doing population level digital twin studies and linking those population level studies down into genomics, which is an exciting opportunity, I think. So what we have is this measurement of the kind of ECG, and if you've seen any medical drama, there's always a blipping line on the screen, and this blip here, so you can impress your friends, the large blip is when the main two chambers of the heart, the ventricles, are activated. So this shows you that there's an activation pattern in the ventricles, and the width of this, or the QRS width, which are the three labels of the electrode, tell you how long it takes for the main chambers of the heart to be electrically activated. If you have a diseased heart, it becomes very slow. So the conduction velocity is slower, the cells aren't working as well, and this becomes wider. And so we wanted to see what is causing this width in this population study. Is it different between people of different ages? Is it different between people with different genders? Is it different people who are large, who are small? And so we were kind of thinking, what were the things that go into this? So one is this kind of the cellular electrophysiology. There is the tissue structure. Click. There is the anatomy. Big hearts can take longer to activate. Small hearts can take less time to activate. There is the locations of the electrodes that you're going to place in the body. So where you place those might determine how that gets measured. And there is also kind of a fast conduction system, which was kind of cardiac physiology, which might be important. There's a number of things that might be important in this process. What we have, though, is we have an MRI and a single scalar value telling you how long the heart takes to activate. So what can we do? So we can take our MRI, and you can effectively pay a machine learning person to automatically segment that eventually. So I'll segment this. We can do an electrophysiological simulation. We can then simulate the 12-lead ECG, and we can estimate the cure, and then simulate the cure restoration. Then for each patient, we can start linking this cure restoration to use it to infer something about the tissue level properties. But which of those properties can we reasonably infer? What's the most important one? So what we did was we made our models. So the model that we have for electrical activation has 20 different parameters, characterizing the boundary conditions, the timing of that boundary conditions, and the material properties. We then have another 30 parameters which describe how the system is being measured. So each of these points is an electrode. Each of those points can have some uncertainty. Is it higher? Is it lower? Was the person in a rush when they put their leads on the patient? Was the patient large? And there's some ambiguity on where those points are. So we want to see which of these parameters are important. Again, because we have no imagination, we use Gaussian process emulators and sensitivity analysis. It's a go-to, it's a hammer. It's great. We do our analysis, get our sensitivity, and identify which of these parameters are important. So we can look at all 20 of the different parameters, and because we didn't know if this was going to be important for one patient or another patient, do the whole process on 10 different patients. All of them, we identified that the kind of conduction velocity of the myocardium was most important for this cure restoration. Also, when we repeated the whole process for the measurement indices, the conduction velocity was again the most important parameter. So we wanted to use the cure restoration with the anatomy of the patient's heart to estimate what this cure restoration was going to be. And so the challenge we have is that we have anatomy with about 8 minutes. To estimate conduction velocity per case, we're at about just under 15 minutes. And so we have a 64-core machine, which are nice kind of workstation machines, which you don't have to pay for air conditioning if you buy them. And we can do 100 patients per day, which is great until you have to do 100,000 patients, and it's going to take you 1,000 days, and it's going to take you 3 years to process the UK Biobank, or 1.5 years if you only do the 50,000 cases I've got so far. And you can buy more machines, but it's still, computationally, this is a challenge. And again, Very happy for thoughts on this. But what this allows us to do, and so we've done this for about 4,000 hearts so far. And so this is making 4,000 patient-specific models, which have been calibrated both for anatomy and function. And we can start to look to see if males or females, overweight or obese people, people of different ages, have different material properties. We see that there are big differences in the QRS duration. So there's statistically differences in the QRS duration between male and female. So females tend to have faster activation. And we didn't know if that was because they had different conduction velocity materials or because they had different sized hearts. And the explanation was that the material properties are the same, but the hearts are just smaller, which is not surprising, but women tend to be smaller. If we did this between Caucasians and kind of Japanese people, we would also find that the QRSs are smaller in Japanese people, tend to be smaller. For the obese, again, we start to see changes though in the conduction velocities. We're starting to see changes in the material properties, and likewise between different age groups. So this was an interesting way where we can take this kind of idea from patient-specific modeling and moving it out from the clinical side up to the population scale and start to think about how we can use these models on a much wider basis for doing genomic studies or asking population level questions. But yeah, it's going to take too long to calibrate. If we take the idea of calibrating one parameter, which is 100 cases per day, to the 45 parameters, which is 1.3 million core hours per case, these things are mutually inconsistent. And this is not adding in shape into this either, shape uncertainty or variation in shape. So I see there being a huge opportunity. I see that we have the data. I think we have the simulation tools. But I feel like the computational statistics and how we're going to deal with some of this uncertainty, how we're going to quantify sensitivity, how we're going to calibrate these models, there's lots of room and lots of opportunities for improvement here, particularly when we think about these kind of networking ideas where you can have large numbers of models of similar systems, and we want to see how can we network information between those together to be much more efficient in calibrating those. And I think if we're going to scale digital twins from bespoke solutions where we have today to wider solutions, then these are kind of some of the challenging or, for me, interesting statistical questions that are available. And so this was a paper that we did on for teens on what we're really thinking on doing. This is our representation of our doctors, which is probably a fair representation gender-wise, but aesthetically fair representation, trying to play a computational model of the heart to improve it, to make it better. Thank you.
Thanks very much, Steve. Lots to think about and discuss. Any questions?
Can I provoke you into giving an opinion about what kind of computational methods are going to work here? So obviously at the moment using lots of Gaussian process approaches, which are black box, zeroth order, and sit on top and get criticized for all kinds of reasons, as you've said. Is that the only kind, are those the only kind of methods that'll work, that just take simulation outputs, or is there scope for getting into the models and more intrusive kind of methods?
I mean, I'd pass that question probably on to my statistics collaborator, which would be you. So I think the challenge we have is that the simulations are complicated, and they have models which are being calibrated and tuned by kind of numerical analysis and high performance computing people, and those people are very interested in their problem, and they're doing quite a good job at solving it. But that means when they deliver something to you, it is wrapped up with a bow around it, and you don't really have the competency, the energy, or the budget to take it apart and put it back together again. And so I see that the black box approaches, I struggle to see how we're going to move away from the black box approach. And it would be nice not to use that, and maybe that new software will become available and it will all become easy, but it has as yet to become very easy. And we have two collaborating groups who do all of the software for us, and that runs on HPC. It runs pretty reliably, but we don't want to have, in my group, I can't afford to employ another 10 people to be doing software development on simulators to keep that going. So unless commercial companies make a way of unpacking this and putting it back together where you can pay a licensing fee for that access, I struggle to see how within an academic space that's going to work, but very happy to be wrong.
Maybe I can ask one. How necessary is it to run these simulations on everyone in the UK Biobank? I mean, some of these people are going to be pretty similar to each other.
Yeah, so I don't think it is going to be necessary to do that, but I think it's how do you quantify how similar someone is, and there might be subtleties, there might be what have you, and so that's working out how to quantify how similar someone is to everyone else, and then how you can reuse simulations from another patient to calibrate a model for a current patient, or if we just have bins that, you know, you're a patient who has these key demographics, and we can then just say you fit into this bin, and broadly speaking, the material properties for everyone in that bin are going to be similar, and it's not patient specific, but it is sufficiently specific that it's useful for our applications.
Okay. Just for convenience, I'll go to Edward.
Yeah, thank you. So the forward models are electrophysiology coupled with cardiac mechanics?
Yeah.
And that's finite deformation?
Yep.
It must be, yeah. So it's not so easy to, if you're a linear adjoint would just, you know, and that's actually their self-adjoint, but no, that you'd have to linearize and
it's all coupled together in a relatively messy,
I'm sure,
way. So
yeah, there's no, it's not
it's
like
not easy to untangle it.
Yeah. It's not a residual written in one place where, you know, the residual of all the equations is available. Then you can hit that with automatic differentiation, maybe at the element level. But this is probably the output of this goes as input to that, and this cycles back to this. And
yeah, I think you've got a cellular reaction term, which is fantastically nonlinear.
Yeah, ODEs.
And ODEs, which all the information is then moved between those.
Yeah.
So it takes information from the PDEs, come down to ODEs,
right.
Fantastic nonlinear, effectively transform, and then go back to the PDEs.
The reaction term.
Yeah.
Okay. Yeah, it's a mess.
So if you make some bold assumptions about how tension is going to be generated, and you make some bold assumptions about linearity, then people have been doing adjoint methods, and they work really well, but not for the full problem. And so maybe we need to break the problem up, but then you're taking it apart, doing one thing, and then it's not an obvious solution. It'd be nice to have a kind of a complete solution.
Right. And automatic differentiation isn't going to help, because then you're different. I mean, presumably these are implicit solvers, right? It's reaction diffusion equation. And so you don't want to automatically differentiate through, you know, Krylov or you know.
No, I mean, we have looked at doing that for some of the ODE models,
right. The ODE
and
model, that's okay. Yeah.
That's been, I would say, tedious. But that at the cell models you can, but it does, you end up with big equations.
Yeah, I'm sure. Yeah. Okay. Nice talk.
Yes.
Yeah.
So actually, I have several questions, but maybe we can take it after.
Yeah.
So for this, you started with this very big picture of digital population,
Yep.
and you focus on some part of that picture.
Yep.
So, for example, in the network of digital twins, what is missing? I mean, what is your vision for that?
Yes, I mean, so with the current approaches we have, I said it's 1.3 million core hours to do a sensitive analysis. That's not, the calibration is on top of that. And so once we've calibrated that one case, that's fine. But our clinical studies are 70 patients, and Archer 2 are very generous, but they're not that generous. And so we have to find out how we can reduce. We cannot do kind of a couple of thousand simulations per patient. And so that's where the networking is going to come from, just in the first instance, without those trajectories, but just from calibrating at a single time point. Can we take patients and try and reuse are we either going to reuse simulations from one patient to inform another, or are we going to make some type of global GPE over anatomy and material properties that we can then use to calibrate every patient using that one GPE in the first instance? So those were the two thoughts that we had. Happy for others, but that's kind of what we're thinking of. So that's where the networking starts to come from in the first instance. If you go forward and you say, I think of a patient who is about to start a drug, and you want to know how likely are they to respond to that drug. If you had digital twins of a large number of patients, and you could find someone who had very similar demographics, who'd started that drug 6 months earlier, then you would have tracked that patient and have information about how that patient had responded to that drug, and how to use that information to improve the forecast of your new patient. And if you have that kind of network of digital twins in that environment, through both across patients and through time, then you have kind of information from almost like the future which you're trying to bring into the patient currently, and how do you do that? So I think there is questions about how do you fit across a network of digital twins, how do you filter across a network of digital twins, and how do you forecast across a network of digital twins?
Thank you. I was wondering, do you use the sensitivity analysis that you do to construct the Gaussian process emulators? So using the fact that you know that some parameters are more important than others, do you explicitly incorporate that in the emulator?
So in some ways, yes. So normally we've created the emulator to do the sensitivity analysis and the submodels, and then we throw out the parameters which don't seem to be very important for the information that goes from one submodel up to the next layer. And then we only perform the generate Gaussian process emulators on those parameters at the higher layer, which seem to be important based on what happened at the lower layer. So in that sense, yes, but I could also see how if we were doing this in a loop, we could then, having done that sensitivity analysis, we could, for calibrating, we could throw out the parameters at the higher level, which aren't important, rebuild a GPE on that subset of ones that were important, and that might be more efficient for doing for calibrating the model. So that's something we'll be looking at. But if I've missed the question or there's another way to do it, again, I'm here looking for answers.
So you're only using it in kind of a yes, no
Yeah.
fashion, right? So either you include the parameters or not, but you don't assign like different weights
No.
in the kernels or things like that. Okay. Thank you.
Any further questions for Steve? Mike.
So you were describing before the problem of trying to predict the holes of those simulations that don't work. So, so when you start running one of those simulators, say you have a set of parameters that you fit into the simulator, you run the simulator. Isn't there a way to predict in that running time whether the simulation is going to work? I mean, like building. I mean, I don't know how the simulators work, so they go iteratively.
Basically, it iterates long, and you sit there desperately watching as it goes from 1 millisecond up to about 500 milliseconds was the simulation time, and you kind of crossing your fingers because it's a nonlinear solve that it's going to converge all the way through and give you a result that's going to be a sample. But again, they're large, complicated systems, and so it's hard to predict precisely when it's going to work and when it's not going to work. And we've gone through a number of processes where we have done verification tests, where we've had lots of groups solve the same problem to make kind of idealized questions. And when we've done that process, people have normally found various subtleties in the numerical methods that they've been using, which has led to increased errors or not. And everyone's had something they've implemented themselves and it's all worked great. And then when we compare to everyone else, it's like, oh, you've done mass lumping at this stage or just implicitly, and that's changed the numerical accuracy. So it's quite hard to work out what's going on in these systems. And so we have a lot of testing, but there can always be more.
Thanks, Steve, once again for his talk. Okay, so let me introduce David, David Wagg. David's a professor of nonlinear dynamics within the Department of Mechanical Engineering at and like Steve, in fact, David is one of the co-directors of the new Turing Research and Innovation Clusters for Digital Twins. So it's our pleasure to have David here today.
Hi, yeah, thanks everyone. Thanks, Chris. Yeah, I'm David Wagg. I'm one of the co-directors for the new TRIC. As has been mentioned, I'm going to talk today about a time-evolving digital twin for engineering applications. I should manage expectations. It's difficult to follow Steve. I'm not going to show any more of those really, really nice color pictures and so on. So, but I will try and say some things which are potentially interesting. So just a bit of an overview. I'm going to give you a bit of background and context. And of course, like most people do, they try and sort of explain what they mean by digital twin in the context that they're working in. So I'll try and do that. And then we'll move on to looking at digital twin in a time evolutionary sense. I'm going to introduce this idea of digital twin output functions, which isn't really anything new. It's just something that's borrowed from control theory. And it's a nice formulation that we've been using, that we found relatively useful. In that context, I'm going to talk about how I'm going to set up some performance measures and do some weighting or optimization to basically blend models together to create these output functions. And then I'm going to quickly move to a sort of an example, which is relatively simple, this cascaded water tank system, which some of you may have seen before. And then I'll talk about some of the details associated with that, essentially. So digital twins, I've shown this slide before, for those of you who've perhaps seen some of my talks in the past. So I'm a dynamics person, so my background is nonlinear dynamics or dynamical systems theory primarily. So, I come from the tradition of trying to make physical models of systems and, acknowledge that they might have, nonlinear behavior and so on. So I'm interested in dynamics. And of course, I think digital twins are naturally a dynamic kind of phenomenon. Mostly people want something that changes with time over the time period of the physical twin. And this is the basic setup, right? So we've got a physical twin, which in my case, I'm an engineer, so it's generally an engineering structure or artifact of some kind. And we've got this sort of two-way interaction. We're going to take data from the physical twin and maybe other information. We're going to try and use that in combination with lots of other things to create a virtual representation of it, which we call digital twin. And then we're going to use that to kind of control or design or operate the asset in some way. And so, the headline is it's a virtual duplicate, if you like. It's it's a very versatile and universal concept, which is why it's getting applied in so many different contexts and why people are so excited about it. Previous to digital twin, we used to talk about dynamic virtualizations. And given that digital twin, spans such a wide area, sometimes I wonder whether it might be better to have some sort of subterms. I'm sure that one's too much of a mouthful to catch on, but that's what we used to call it. So it's like trying to create virtual versions of dynamic systems, essentially. So another way that I like to think about digital twins is like in cooking. Okay, so I think a lot of things can be explained by ingredients and recipes, and this, in some sense, again comes back to why so many different people have different ideas about what a digital twin is. So this kind of picture tries to sort of explain what I think the ingredients are really. So this is not a recipe. This is like a picture showing ingredients. So models, data, some way of connecting through some connectivity, which is usually a network of some kind, and some knowledge. Okay, the kind of ingredients that are kind of fundamental. And then there's also to create this thing, if you create workflows, if you want to call it that. I know some people don't like that term, but some kind of process control and optimization. So these are usually the kind of things that we're borrowing. These are our ingredients, if you like, that we're trying to bring together to perform some digital twin function. But the question is, what's the recipe, right? And so the recipe is a lot less clear, I think. I mean, actually, Steve did a good job of explaining what his recipe was, or some parts of it. But in a generic sense, what's the recipe for a digital twin? I think that's that's a pretty open question, particularly if you want to describe it mathematically. Okay, so I think that's something that's really interesting to me. So this normally when we give presentations about this in an engineering context, we show pictures like this, and this is about as eye-catching as my slides are going to get. So that doesn't really compete with Steve's hearts and beating and so on. But this thing here is a decommissioned Hawk aircraft. So this is a T-1A Hawk that was it's been painted several different times. All right, so during its life, so it was in the Red Arrows at one time, which is the kind of flight display team that the British Royal Air Force have. It also had a kind of camouflage combat livery as well. So at the moment, it's decommissioned. It doesn't have an engine anymore. It was donated to the laboratory that we have in Sheffield. So we use it for sort of dynamic testing and so on. So, it's an interesting structure, but it's a legacy structure, right? So there's no digital representations of it. There's no CAD, there's no FE models, nothing like that. Of course, you can't really see the inner structure of it without sort of trying to X-ray it. So it's difficult to reverse engineer any of that. So, I need to manage your expectations. We haven't got a really comprehensive digital twin of this, but we use this as a kind of concept for, in engineering terms, how might we build a digital twin and how might we use it? And of course, from an engineering point of view, what people tend to do is they just start plugging things together and see what happens, essentially. So, one way of having your recipe for a digital twin is to do what we've done here and just kind of get together with a group of other people. So we had a data sharing company called Iotics who were, for example, wanted to collaborate with us. So we set up a data sharing platform where we could have remote hosts working in different geographical locations. We've got some work going on where we've built this sort of web-based user interface. So we've got a sort of user interface. We've got this sort of very, very rudimentary finite element model. And this user interface has some Python code sort of routines that we built into it. So it can do these types of things here. This is GVT means ground vibration test. So we set this up, to do a vibration test. And so one approach is just to sort of plug and play, right? Software carpentry or whatever you want to call it, just to try and assemble things and see what happens. There's lots of people doing that to varying degrees of success. So what we tried to do a little bit differently was to kind of peel back the layers and look much more simply at a very, very simple rudimentary kind of concept and try and do a little bit of thinking about how we might put some maths against that. And there isn't really any maths. Maybe there's some mathematical symbols and terminology, but there isn't really any startling maths. So again, to manage your expectations. But this is the kind of concept. So this is a very simple way of looking at a digital twin, right? So the physical twin is in an environment. And this is the first problem we get. Often the environment is forgotten about, but it's always usually in a sort of large scale structures sense or infrastructure sense, the environment is usually really significant. And we want to create a digital twin. So we might want to create a simulated environment, but as I say, often that's forgotten about. We can take data from this physical twin and use that in our digital twin, right? But we're also going to identify some quantities of interest. If in some sense we want to try and compare, and I think again, lots of other previous talks have said that's what they're aiming to do, right? So they've got some quantities of interest. And of course, these are linked, these must be linked to the real purpose of what you want to achieve with a digital twin, right? So you have to have an aim and a kind of real purpose, and that would inform what your quantities of interest are. They'll essentially, I'm assuming they come from the data that you can gather. And your digital twin, you want some outputs that you're going to, you meaningfully make comparisons with. Right, so the output functions idea is that we're going to create some functions, kind of mathematically, if you like, and those are going to be like outputs that we can create a sort of one-to-one map between each of the QOIs that we've got and these outputs, so that we can then make some comparison. And of course, usually when we've done a comparison, it would be usually part of a validation process of some kind. We usually want to use that information to then go back and update our digital twin. Usually, model updating is one way to do it, but there might be other ways that you can use this information. Usually our performance is limited in some way, right? So we might be able to then make improvements. But then really the kind of key idea is to, to give these outputs in a kind of meaningful way. Now there's lots of, I said that the outputs and the QOIs had to kind of relate to some defined objective, and we came up with three, of which the simplest one is the one I'm only going to focus on, right? So the simplest one is to just emulate an input-output behavior, okay? And by that I mean inside the digital twin, we could have all sorts of things going on, lots of different models with different local sets of states that we don't really care about. We just care about the fact that we're putting in something and we're getting out something. We're just trying to match what that is. So we've got, the physical twin, we've got some input to it, some output. We're going to make a digital twin. We're going to try and emulate that behavior without really caring about anything else. Of course, the next obvious step would to actually start care about the internal states within the digital twin, right? So can we then, so I've called that simulation. This terminology is probably, kind of not always appropriate. It might be there's probably better ways to describe this. But the next level up would be to match the input-output behavior and have some matching of the internal states as well. Which would be, if we've got this sort of lots of different models, all have potentially with different local sort of state vectors and so on, that might be quite complicated. And again, I'm not going to claim that I can do that or talk about that today. But then beyond that, we want to make predictions with these things as well, right? So we want to match input-out behavior and the internal states, and then possibly make predictions beyond the context of where we've kind of validated our digital twin, right? So these are sort of ascending levels of sophistication as far as I can sort of think about it. And I'm just going to talk about something to do with the first one in this talk. So I mentioned, we got this sort of cooking analogy, right? We've got our ingredients, we've got our recipes, and we're going to mix it all together, and we're going to make a kind of workflow or whatever. So this is an example of one potential workflow. And obviously this is all context specific, so it depends on what your particular application is. And I haven't said what that is here, but I'll try and just sort of explain a little bit of the context in this sort of diagram. So physical twin here, and in the engineering context, we often have some sort of local hardware, which is usually embedded or attached or close to the physical twin. So these are things like sensors and data acquisition systems, local real-time control processes normally, and then sort of controllers and so on hardware, which are feeding back, locally all the time, often in real time, typically. Okay, and this is what people talk about, and when they talk about on the edge stuff, they mean doing it here, right? Okay, instead of doing it somewhere else, like that's remote from the physical twin. So this is our local stuff. Essentially, you can assume that we don't care about this. That's what we're going to do for this talk anyway, and that the data is kind of coming through this, and we can then use it in some additional processes, right, which are not necessarily in real time. And in fact, what we're going to do is we're going to segment the data into chunks. Okay, that's what these kind of like this diagram is supposed to represent. So the data points are coming in at some I1, 2, 3, and then there's going to be J data segments that are going to accumulate continuously. Okay, and then within each data segment, we're going to carry out some kind of workflow. Here, for example, we've got sort of some combination of physics and database models, which are going to be selected or ensembled together, and they're going to be create output functions, which you give to the users. And then, of course, the users, we're assuming that they're humans and that they're going to make some decisions. And then these are sort of control decisions in this context, which then comes back to here, and there's a sort of continual update and so on. But one of the points that I wanted to make is that this idea of sort of doing things in data segments is quite important, because on a digital twin, if you're deployed across a network, and you've got to keep doing this, right? Okay, I think a lot of methods that we might use assume that you've got the luxury of looking at your data for as long as you like, whatever you want to do with it, spending a lot of time with it. In this kind of scenario, there's a kind of time pressure. It's not, the real-time pressure would be here, right? You have to do everything within a time step. But then if you want to do something on different timescales, which aren't real-time, but there's still some urgency to them, they have to be done within a reasonable time frame that's appropriate to the application. Okay, you're only going to have a limited amount of data to do it on. And you've got previous data sets if you want to include them. But you most usually you're going to be looking at the current data segment. Okay, so that's a bit more context to this scenario that we're going to look at. And as I said, we're going to just kind of ignore this control bit for now, and just kind of look at the data flow that's coming out sort of in a forward direction. That's the plan. So I mentioned quantities of interest. So one easy way to do that is we're just going to have a vector of them. I don't think, hopefully that's not too controversial as the starting point. But they're kind of physical quantities in the context that I'm working in. They would be things like displacements, velocities, maybe accelerations, strains, other things. Okay, but they're things that we can actually measure from the physical system. And then there's going to be a sort of time base, and we're going to say that there's a sort of start and an end of the digital twin, right? In a time sense, you're connected or tethered to physical and digital twin, right? And you might be able to start and stop this. So you might have multiple periods of time, but I'm just going to assume there's one period of time during which you're tethered together, right? You're connected together, and all of my data segments are going to happen within that time interval. So the output functions, this is really the basic idea. And as I say, this is not a new idea. It's just borrowed from control theory. So in nonlinear control theory, if you're doing state space control, you assume that you have a differential equation, which operates on a state vector. And then you make the assumption, which is interesting from a control theory point of view, you often can't get access to the states, right? And typically so you have an additional equation, which is of this type of form, where you have an output function, right? So your outputs y are some function of something to do with the system. And I've introduced here, I'll tell you what some of these things are in a minute. But in the control sense, you might be able to make a measurement, and then to kind of work out what the state is, you have some functional relationship between what you've measured and what the state is. And that's what this type of equation is trying to denote. And basically what I've put in the brackets here is M is a library of models, and then D is the database with all the data segments in it. T includes the time-based information that we just mentioned. This chi thing is a set of all the sort of hyperparameters, all the optimization parameters, weightings, and so on. And then Ti just says that it's evaluated on at some point in the time interval. And I think so this probably just says that there. Okay, so the idea is that we're going to try and get these outputs. So these outputs are designed. The y vector is designed to map directly onto the z vector. Okay, so we can compare Y and Z, the QOIs and the outputs. We define them. Okay, and so we can look scalar by scalar at each of those things. Okay, but obviously inside here we have higher dimensional things going on. So what's in, what are they actually made of? And so in this example, the output functions are basically a weighted ensemble of some model output functions. Okay, so drilling down, I'll show you a picture in a minute. We're going to have this library of models. And again, we'll do the same thing with the models. We just say for each model, we're going to select an output. And then to create a digital twin output function, we're just going to ensemble some of those together, okay, to create the digital twin output function. And again, you can probably guess what these, this is at the model level. This is, X is the states, and theta is the parameter vector, U is the kind of inputs, D is the data sets, and so on, right? So hopefully there's that sort of makes sense. So obviously, that kind of control theory stuff, state vectors and state equations and output functions doesn't take any account of uncertainties. Okay, so we want to put this into some kind of statistical setting. I've called it a model. Maybe it's not a model. Maybe that's the wrong terminology. But essentially, what we used is just this is, I'm sure this is very familiar to people. I came to this sort of through the Bayesian calibration type of approaches that are well known. And again, this is just borrowing that kind of formulation to fit the purpose that we had here. So Zi is just one of the quantities of interest at time step I. And what this is saying is that we've got some output from a digital twin. Okay, so normally this is just a computer simulation. Okay, and we're just going to account for the epistemic uncertainty and the aleatory uncertainty, or the model form error. So delta I is some representation of the fact that our digital twin output function is going to have some model form type error in it. And then there's going to be some other measurement uncertainty as well. So we will also try, we will add parameter uncertainty in as well, but we'll do that inside the models. And so I'll talk about that in a minute. So in this model library, if you want to include parameter uncertainty, that's also possible to do that. So obviously there's a lot of theories associated with this formulation. I'm just going to totally ignore them and just abuse the notation completely. And I apologize for doing that in advance, because I'm not going to. So for example, I'm not going to suggest models for the uncertainties that are explicit or anything like that. Okay, so I'm just going to use this framework to acknowledge that they are there, and then I'm going to just do some relatively crude things to estimate some errors essentially. So hopefully this picture might try and be a little bit more about what the method is. So we're going to collect data, we're going to process it. Some of the data we're going to select out as our QOIs, but essentially we're going to just segment the data and put it into a database. At the same time, we've got a model library. This suggests we've got lots of models, but actually in the example I'm showing, I've only got 3. These can be data-driven models or physics-based models. Okay, so and then you're going to use the data that you've got. Obviously, some of the data will go to the data-driven models, but the data and the models will essentially be used in some optimization process. The optimization process will just choose weights, and then that will go into some sort of selection ensembling type of operation here. So the outputs of the models will feed into that. And as I say, so each of the models will have these output functions, and they'll be ensembled into some digital twin outputs. Okay, which then we can use in a validation process to compare with the quantities of interest, essentially. So that's kind of, hopefully that's the idea in a nutshell. And there's lots of choices here about how what you actually do in this space. We've made some choices which I'll show you, and I'm pretty sure that probably they're not always the best choices, right? So I'd be interested to hear if people have got suggestions for better things. So this is what I'm going to do with my error measures. Essentially, I'm just going to assume that my combined uncertainties are equal to the difference between what I'm measuring on the quantity of interest and what my digital twin output function would tell me. Okay, so I'm just going to use that as in a crude way to create a measure for error, essentially. So what I'm going to do is over the data segments. So this is like we run this over the data segment. I'm just going to look at this as an error measure. And what I'm going to do is I'm going to sequentially test each of my models. Okay, so this I've shown as the as the digital twin output function. But in the algorithm, what I do is I run each of the models here. So I test each of the models against the current data that I've got in the data segment. And that gives me some measure about how good is that model at predicting that particular QOI, right? And then I put that into that information goes into the optimization to choose the weights, okay? So that's what we did, and it's pretty crude, right? Because I'm sure there's more sophisticated things that we can do. One of the problems with this is if you're trying to emulate, which is what I said I was going to do at the beginning, this always tends to bias the database models as the best, right? Because what the database models are doing is that they're just fitting to the data that you've got. And of course, some of the physics-based models are not doing that. The physics-based models will usually will have more error, okay? So if you want to just emulate, that's fine. Okay, so what you tend to do is you tend to choose the database models. If you wanted to have predictive capability, so you wanted to have more of the physics-based models in the outputs, then this optimization criteria would be not the ideal one to choose. Okay, but this was a first pass, so we just used something very simple. Okay, so what we did was we introduced some row functions. Okay, S and P. S means which data segment you're operating on, and P is which model is being considered. And essentially, we then are trying to relate our particular measurement of the QOI to some weighted combination. So this whole first bit here, this is just a weighted combination of models. And some of these weights could be zero in terms of, it could be some sort of hybrid selection ensembling, right? So you might have 10 models, but you might choose to ensemble just 2 and zero out the rest of them, or whichever you choose. This is slightly misleading because this term, now of course, each of these models has some epistemic uncertainty in it, some model form error, and I've just kind of grouped that all together into one term, okay? Because I don't really I'm not postulating a model for that. I'm just using it to show that, you know, it's there in our formulation. This is just the combined epistemic uncertainty of all the model outputs. And then I'm just saying that my digital twin output function is just that ensembled together model, essentially. And of course, they're all trying to predict the same QOI. Okay, so maybe I didn't make that clear at the beginning. So the reason I'm testing each model against a single QOI is that they're all trying to predict the same QOI. Okay. So it's quite a labor intensive. So another drawback to this is it's quite labor intensive or computationally intensive kind of process. And then, as I mentioned, to choose the error, I'm just using this kind of very, very simple idea that we've got a weighted sort of sum of errors with a constraint that obviously our weightings have to sum up to 1. I'm pretty sure that this is really limited, okay? And I'm sure there are much better ways of doing it. So I'm not advocating that this is a good method, but it was just a very simple way to get started, essentially. So let's have a look at a physical system which isn't an aeroplane. Okay, so this is a cascading water tank system. I think it was mentioned before. I think you mentioned you're familiar with this system. Okay, so it's really popular in control engineering, and you know, maybe in some other contexts as well. So basically, this is a photograph. So it's a real system. You can get the data from online if you want to also use this data. It's used. It's taken by some. This was built and the data was taken by a group in Belgium, and I'll give you the reference in a minute. And it's been used for some sort of system identification type conferences where people come together and they have a data set that's given out, and then everybody has to present their best guess at identifying the system. So this was one of the systems that was used at one of those conferences. So the basic idea is you've got a reservoir down the bottom, you've got a pump here. The pump just pumps water up into the top tank, and then there's a flow of the water out of the bottom of the top tank. You can see it more clearly on the schematic, into tank 2, and then out of tank 2 back into the reservoir. Okay, and the reason that this is quite a nice system from a sort of control and dynamics point of view is that it's relatively simple, right? So you can write down an ODE model, which I'll show you in a minute, which is relatively simple, but it's quite strongly non-linear as well. And to some extent, it has uncertainties depending on how you want to model it. And there's also possibilities of things like overflow happening as well. Okay, so you can set scenarios so that the tanks overflow and they come out, the water comes out of the top of the tanks and then goes into the reservoir. And then obviously that becomes even more complicated. You can either treat that as an additional kind of non-linearity or uncertainty, depending on, you know, how you want to try and model the system. And so I think this just summarizes that. Yeah, so we're going to have a control which is called U or U1. So that's the control input, which is going into the pump, pumping the water up, and then tank 1 water flows out into tank 2, and possible for overflow to happen as well. So this is an example of one of the input signals. So this is the reference from the team who have generated this data, and like I say, you can it was used for that workshop on nonlinear system identification back in 2016. So this is just one of the records of the input signal that we'll use in our simulations. So as I said, that there's some relatively simple physics-based models. So this is sort of the basic ODE model, and you could say, you know, we've got 2 states here, X1, X2. They correspond to the water levels in the 2 tanks. Okay, so X1 is the tank level in tank 1, X2 is the level in tank 2. You can see you've got these square root nonlinearities here, which are kind of a little bit unusual, but that's why there's a sort of strong nonlinearity. And then we've got the K scalars are the parameters, or the kind of the physics-based parameters, and sometimes there's some uncertainty sort of noise included. It depends on the context whether you use that or not. And yeah, the U input is here. Okay, so that's the input essentially. So we can create a parameter vector here, and as I said, and I'll mention a bit more in a minute, what we actually used ABC for the computation of this, so we included sort of uncertainty on the parameter vector as well. So that was the sort of way we operated. So if there's overflow, then you can modify that ODE model and add in a kind of conditional effect on this second differential equation, so that if overflow happens, when the water tank tank 1 goes over 10. Okay, and then we get an additional term in here, which captures some of those additional nonlinear dynamics essentially. But as I say, so we'll see. We use both cases, and so you can just put all these models essentially in the model library, and select them depending on what's appropriate essentially. So as I mentioned, we use ABC. Again, it'd be interesting to hear people's views. I know some people don't like ABC very much, and it is quite computationally intensive. We were conscious that we wanted a sort of quick and relatively easy thing to, well, whether quick is the right thing. Quick to apply, it's maybe not quick to compute, right? So the computational cost of ABC is significant, but we wanted to be able to include the parameter uncertainties. And there's a kind of philosophical point, which is interesting here, which again, others have probably thought about this, but sometimes you see people with ODE models in this kind of context, just doing deterministic simulations. And then there's a question of like, well, can you know, is it a good idea, or is it a valid idea to try and combine something from a deterministic simulation with something from a probabilistic simulation? Okay, so we decided that what we wanted to do is to kind of put these types of models within some kind of probabilistic setting of some kind, or you know, acknowledge uncertainties within these models in some way. Okay, so that's why another reason why we chose to do ABC on this, and actually use sort of distributions to represent the parameters rather than just taking scalar values, and you know, assuming there's some sort of deterministic output. You could of course use these like these sort of noise parameters would be another way, but you know, there's some interesting questions there about, are you trying to, within the digital twin, how are you trying to capture the uncertainties if you've got a model library with lots of different types of models? And anyway, that's something we thought about. But
so you would randomly change the parameters while you simulate the ODE, or you fix them?
So in the ABC, you choose an initial distribution, and then you randomly sample. It samples from.
It's Bayesian inference, right? So
yeah.
You estimate the parameters, and you get a distribution of the parameters.
Exactly, and then you end up with your posterior distribution you've computed, right? Exactly.
But how do you input them into the ODE when you simulate your model?
So you just have an algorithm which just selects them, just like some trick.
distribution of models, actually.
Yeah, if you want to see it like that, yeah. I mean, I think about it as a model with a distribution of parameters, but yeah, I mean, this thing here, these things here are distributions.
But then the simulation is still deterministic. You choose the
Yeah.
parameters randomly, but then the rest is deterministic.
Yeah. Then you just use an ODE solver,
Okay.
and then you either accept or
because you have model errors there as well. The W's, I mean, model errors, right?
yeah. These terms are again I think I need to check, but I think they're set to 0 in those things.
Okay. And then
They're possibly, you know, you could possibly add that to represent noise within the, you know, within the data gathering or the experiment or something if you wanted to. But
and then you have the internal states on top of it.
Yeah.
I mean, okay.
Yeah. But the question is, I guess the question is, what's the best way to represent this if we're trying to acknowledge that there's uncertainties in the system, right? So what's our confidence of these parameters? Probably not that they're scalars, right? That's
just,
yeah.
For me, it was just to clarify.
Yeah. Database model. So we had one database model in. So we had these two ODEs and one database model. This was a NARCS model, neural network. This was done by one of my co-workers on this paper. So I'm not so sure about the details of it, but it seemed to give generally this was the model that was most closely accepted, right? Because as I said before, what was happening is this was fitting to the data that was given. So when we did an error measurement, it said this is the best model, whereas the others had some assumption of physics. So we put that into this sort of what I call the statistical model or statistical setting, where you know we're looking at this quantity of interest. The superscript means that the second in the vector, so this is water level 2. I'm sorry, there's lots of superscripts and subscripts here, which make it perhaps difficult to work out what's going on. So this row weighting is for the S data segment. It's associated with the second model. Okay, so it's a non-zero weighting coefficient that then is multiplied by the output from the second model. This is from the third. This is for the third model. This is the output from the third model, but they're for the second QOI, which is why you've got superscript of the QOI there. Again, this term brings together, this is the merger of the model form error from those two, essentially, and that's how we're trying to represent that in this particular application. Let's have a look at some results. So this is a situation where we've computed, we've selected model 1 and model 3. So we've got one physics-based model and one database model. Again, another philosophical point is, for a digital twin, it makes sense to me to use a database model and a physics-based model. In this context, I don't actually think it makes sense to have two physics-based models, right? But anyway, another philosophical point to think about. Perhaps it's known already, but I haven't haven't thought about it enough. So what you can see here is that the blue curve is the QOI as measured, and you can see that over 10 here for this water level, there's some overflow. So that's why these things go flat here. You can see that the orange curve is the physics-based model that kind of projects past that. The database model does better; it's fitting to it. Essentially, that's fitting to the curves, and these vertical lines are the sort of data segments. Okay, so that's how this. So this is like testing the models. So I've got these different outputs from the two different models I've selected, and I'm just testing them to see how they perform against the QOI for each of the data segments in this particular plot. Okay, and this is the same thing, but now I've created a digital twin, and what I've done is that's the ensemble of the two outputs. In fact, this output's showing the physics model M2 with M3, but it's the same concept. And it should be pretty clear that you can see that the digital twin does a pretty good job, right? Because it's chosen to try and match with minimum error. You can also see that the physics model actually, so there's sort of some jumps here as the data segments change. You can get some or it looks like non-smooth jumps, and that's just because we're changing from data segment to data segment, and there might be ways of smoothing that out. By some, for example, having a data segment here which includes some of the previous data segment or some, finishing values from here. We just did a very naive approach, but there's probably much better ways of doing this type of thing.
Can I just ask again a question? So how would you predict the weights? I mean, if you go into the future, then you have to decide how you're going to combine the models. And retrospectively, you can fit data, right?
Yeah. So we're doing it retrospectively. So we record the data.
But if you really want to say, I mean, in the future, you have to condition these weights on something, right? So Is there any way to put this, or have you?
I mean, my only thinking about this is that we do an initial phase where we try and build confidence in the physics-based models, right, through a sort of series of iterations. We use the data that we're gathering to build confidence. And once we've built enough confidence in those physics-based models, we essentially just have an algorithm which weights those physics-based models much more strongly, so that they are essentially have predictive power, right, because they are validated in some sense against the data that we've seen.
Because here you can see, I mean, in some regimes, obviously the data-based one is better because it sees the cut, which the other model can't see, the physics-based model. And then the other regimes, the physics-based one is the winner, right? So it's not a clear.
No, that's right. So this digital twin, you know, these in some of these sections, what it was doing is it would choose non-zero values for both, but in some of them it would just zero out the physics-based model, right? Because the database model was so much better. It just says, I just select this one. But if you want predictive capability, you're going to have some physics-based model, I think, aren't you?
Oh, right.
So that's, I mean, we get into questions about like, you know, what data you're seeing as well, right? A lot of data we see is what you might call uninformative or relatively uninformative. And if we're trying to extend the capability of predicting beyond the data area, you know, beyond which the data regions are, that's very difficult, right? We tend to want to just interpolate within the regions that we know.
Okay, thank you.
So anyway, I'm nearly at the end now. So conclusions. So hopefully I've shown you some digital twin output functions. I think it's it's like I say, it's not a particularly new idea. It's just borrowed from control, but I think it's has some usefulness to it in terms of a framework. The components in the models were essentially just repeatedly recalibrated or recomputed using these data segments. In the future, probably this raises more questions than it answers, right? Because in the future, we've got to think about these other problems, the simulation and the prediction problems. How do we move to those? And if we do that, how do we, we start to have this problem that we're going to have lots of models with lots of states. How do we manage that? Do we try to have one sort of global state vector that was built from a combination of local state vectors? If we're thinking about that, maybe we have models which aren't state-space based as well. So we have lots of questions about that. And then there's a sort of scaling question, which I think Steve in his talk, gave a great example for. But there's a good question here of like, how does this type of thing scale up? How many models can we include? And if we do that, what computational types of consequences are there essentially? So I just want to mention there's a paper that most of this is taken from, and I didn't do any really of the work, so mostly these guys did most of the work. So thanks very much to them. Thank you for your attention.
Thank you very much, David. We've got 5 minutes for questions. Sally.
Hi, David. Thanks very much for an interesting talk. Look, we're just going on the conversation about models and model uncertainty. So, do you embed model, uncertainty? You could, for example, use your output to attach posterior probabilities to the correctness of a particular model, whether it's a data model or a physical model. And if you framed it in a mixture framework, you could parameterize the mixing probabilities to depend upon the sorts of things that were talked about in the front row. I'm sorry, I don't know no.
So we haven't done we haven't really done that in this context. When I showed that picture with all these data segments stacking up, you can imagine that you've then as that builds up, you can actually start to do things across those data segments, can't you? You can ensemble those together, or is that what you mean?
Yes, you can do it in a formal mathematical way,
right?
That is, right. Got some basis in meaning it for model posterior probabilities. And I was just really interested on the questions that were asked about, because some models will work better in some circumstances than in other circumstances, and then just modeling the mixing. If you modeled it as a mixture model and you parameterize the mixing probabilities to depend upon those scenarios, you'd get a sense of which models work best under what conditions. I just didn't know whether your sort of thinking had gone.
It hasn't. I haven't developed it, but I think, like I said, we started with this idea of emulating, and so our metric was error, just the basic difference between the performance of the model and the measured QOI. But we did think about robustness. as well. So we did think about, how robust were each of the models, and we did a little bit of work on that. But I think, like you say, you can start to build it up essentially, can't you? From
you'd need a few more assumptions around probability structures over models.
Perhaps the interesting thing is that if you want to look at these different things, you want to change those, make those optimization processes more sophisticated. So then have cost functions which include specific terms to try and capture some of those things, I guess.
Okay, thank you.
Actually, also related to this, in machine learning, they have these quite a bit of work on expert systems, right? I mean, how to select the best expert. I mean, your model is basically an expert, and there are, I mean, actually last week I was at the spring school where one of the lecturers talked about this, and under budget constraints. I mean, how many times can you query the expert before you discard him, for example, and things like this. So I mean, there might be some interesting work from there. I mean, of course, it's a much easier or simpler setting than yours, right? So it's lots of IID assumptions, etc. But might be something to look at.
Yeah, no, you're right. The mixture of experts is kind of very similar, isn't it? There's a lot of similarities.
Normally you pick one expert in the end, right? Or in the end you want to find the best expert, maybe.
Yeah. No, I totally agree.
But there's quite a bit of work on this, so be of interest. Yeah.
Maybe I can ask a quick one about, so I think what you described as simulation, which I would probably describe as causal inference. So the what if questions of what if I interfere, and what if I, if I cut off one of the tubes in this, this water experiment. So if I've got a bunch of physical models, these are basically causal models from the stats point of view, right? They encode specific assumptions about what causes what within the system. And if I just train these things on sort of nice observational data, they'll all fit pretty well, and actually might be quite difficult to work out how to weight these things because they all do quite a good job. But those models might give very different predictions of the what if scenario, depending on what kind of causal assumptions, what mechanisms they've got built into them. So does it make sense to model average when you're predicting what's going to happen under an intervention like that?
Good question. You started to bring to mind the Rumsfeld matrix to me, where we had known knowns and known unknowns and stuff, because I always think that probably we're operating in the top left-hand corner of that, right? In the sense of and what we know to be causal and what we can write down as physics models are the kind of known things that we know about. Is that, I mean, I don't know whether this makes sense as an answer to your question, but I guess if we've got those models, they're based on our physical understanding of the problem, right? And so I'm not sure. Maybe I don't understand what your exactly the context of your question, but are you asking about training the models in a setting outside of the one that we know?
Yeah, so if the models have been trained on nice data where no one has come along and squeezed the tube.
Right, yeah, okay. So there's some event that happens that we didn't previously know about, essentially.
And your physical models might differ quite drastically in their predictions for what happens in that scenario.
Yeah, I mean, I don't think we've thought about how to deal with that particularly. I think it's pretty difficult to deal with. I mean, it's except for, I mean, in a structural health monitoring context, that would start to fall into data, thresholds. You have data that you're recording, and if your data starts to go beyond some thresholds, you assume there's something drastically wrong with your system, right? You assume that the system has been damaged or has got, something's happened to it. So then you just usually flag that a human has to come along and look at what's going on, and then they would see that but I mean, whether you can, I don't know that you can do anything like that in a modeling sense.
Any further questions for David? In that case, let's thank David once again.